Welcome to Quiet Universe, where we dive into the strange and mysterious realms of the cosmos. Tonight, we're unlocking a portal to a concept that boggles the mind: wormholes. Imagine folding space like a piece of paper and instantly leaping from one side to the other. These hypothetical shortcuts through space-time could connect distant galaxies or even open the door to time travel. But there's more. Wormholes might be the key to faster-than-light travel. They could collapse without warning, or maybe even connect us to alternate universes. So buckle up, because we're about to take a journey into one of the universe's most intriguing mysteries. Let's explore the mind-bending possibilities of wormholes. Imagine you're standing in one corner of a massive room, and the person you need to talk to is all the way on the other side. Normally, you'd have to walk across the entire room to reach them, taking the long way around. But what if you could just fold that room in half, so that your corner and their corner are suddenly touching? You wouldn't need to walk at all. You'd simply step across the fold and be right there, in an instant. That's sort of what a wormhole does. It's the cosmic equivalent of folding the vastness of space to bring two distant points together. In theory, a wormhole connects two places in space-time, allowing someone, or something, to travel from one point to another without crossing the space between. It's almost like a hidden shortcut tucked away in the fabric of reality itself. And what's mind-boggling about this is the speed at which it could happen. Distances that would take light years to cross could, through a wormhole, be traversed in mere moments. The idea flips our understanding of travel on its head, especially when you think about how everything in the universe is bound by the speed of light as a limit. Wormholes offer a way to cheat that, bypassing the normal rules we've come to accept about space and time. But the human element here is that, while this idea seems like something out of a sci-fi movie, it challenges the very core of how we perceive the universe. We've always thought of space as this huge, unyielding expanse where everything has to follow the rules. Light moves at a certain speed. Objects follow straight paths unless acted upon. But wormholes throw a wrench into all of that. They remind us that even the most fundamental things we take for granted, like distance and time, might not be as rigid as they seem. This idea forces us to question everything, right down to our everyday experiences of moving through the world. It brings a sense of wonder, but also a sense of discomfort, because if wormholes are real, they might mean we don't know as much about the universe as we thought we did. It leaves us standing at the edge of an unknown frontier, where the boundaries of what's possible blur and fade into something altogether more surreal. Time travel is one of those concepts that feels like pure fantasy, the stuff of movies where characters hop between centuries or fix the mistakes of their past. But when we start talking about wormholes, time travel shifts from a wild dream into something that physics doesn't outright dismiss. It's not like we're cracking open a door to step casually into the future or rewind to the past just yet. But the way wormholes bend space-time opens up possibilities that make you wonder. Could time be just as flexible as space? The idea rests on the fact that space and time are intertwined in what we call space-time. When you manipulate one, you're inevitably affecting the other. A wormhole might not just bridge two far-flung points in space, but two moments in time as well. It's a bit like stretching a piece of rubber. You don't just pull one end further in space, you also stretch it through time. If one end of the wormhole is moving differently through space-time, say it's closer to a strong gravitational source like a black hole, or it's moving at near light speeds, time will behave differently there compared to the other end. This difference could mean that if you travel through the wormhole, you might exit at a different moment in time than when you entered. That's where the mind-bending part of time travel comes in. You could potentially jump ahead into the future or loop back to the past, depending on how the wormhole is positioned or moving through space-time. But this is where things get tricky, because now you're not just playing with space. You're playing with causality, with the sequence of events themselves. It makes you pause and think. If we can alter the way we experience time, what happens to our understanding of cause and effect? Could we meet ourselves at another point in time, or undo something that's already happened? Time travel isn't just about technology or physics. It's about how we, as humans, understand life itself. We live with the belief that time is linear, that it flows in one direction and we move forward in it. Wormholes, though, suggest that this may not be entirely true, and that's where the real mystery lies. The idea that we could step outside the normal flow of time creates a sense of unease because it messes with everything we've come to trust about our existence. In trying to grasp time travel, we aren't just thinking about physics. We're grappling with the nature of our own reality. Wormholes might sound like these magical gateways through the universe, but the reality is far more delicate and far more dangerous. Imagine building a bridge out of string. You could cross it, but with every step, you'd be wondering if the whole thing is going to snap beneath you. That's the fundamental problem with wormholes. They might connect distant points in space-time, but the forces at play are so extreme, so tenuous, that the entire structure could collapse in the blink of an eye. In fact, most scientists believe that, left to their own devices, wormholes would be inherently unstable. The moment something tries to pass through, whether it's light, matter, or anything else, the wormhole could implode on itself, cutting off the connection and crushing anything inside. It's like trying to balance a house of cards in the middle of a hurricane. There's just too much tension, too many factors trying to rip it apart. The wormhole might not even exist long enough for you to realize it's there. One second, you're staring into the possibility of traveling across the cosmos. The next, it's gone, leaving behind nothing but the usual laws of space and time. What's fascinating, though, is how this instability reflects the human experience of uncertainty. We're constantly trying to build connections in our lives, whether it's with people, ideas, or even our understanding of the universe. And sometimes those connections are fragile, prone to collapse under pressure. Wormholes are a cosmic version of that fragility, highlighting how tenuous and unpredictable reality can be. Even if we were to figure out how to open a wormhole, we'd still be dealing with the danger that it might close without warning, trapping us or severing the very link we were hoping to exploit. It's a humbling reminder that for all the grand ideas we have about exploring the universe doesn't always play by rules that we can easily control. It's wild, unpredictable, and sometimes it just collapses right when you think you've got everything figured out. Wormholes, in theory, seem like an incredible solution to the problem of distance, but there's a catch. They need something that doesn't exist in our everyday experience to keep them from collapsing. Exotic matter. This isn't the kind of matter you can find lying around, or even see with a microscope. It's the complete opposite of what we know. It doesn't behave like anything we're familiar with because it would have to possess negative energy. Now, that might sound like something from a sci-fi novel, but in physics, negative energy isn't just a plot device. It's a real concept, the one that we've never actually seen in action on a large scale. Exotic matter is strange because, while regular matter, like you, me, or the planets, has mass and therefore creates gravitational pull, exotic matter would do the reverse. It would push things away, like gravity in reverse. This is where it becomes essential for wormholes. Without something to counteract the natural tendency of the wormhole to pinch shut, like a black hole's event horizon, you're stuck with a tunnel that collapses faster than you can blink. Exotic matter is supposed to prop up the walls of the wormhole, keeping it open long enough for something to pass through. It's like trying to hold open the doors of an elevator with your hands, except the doors are trying to close with the force of an entire universe behind them. But think about it for a second. What we're talking about here is the need for a completely foreign type of matter, something that doesn't obey the rules we live by. That's what makes wormholes feel so tantalizing yet so out of reach. Even if we somehow figured out how to create or find a wormhole, we'd be standing there, knowing it's useless without this bizarre material we can't even fully describe, let alone harness. It's like knowing there's a key to the universe's greatest secret, but realizing the key itself might be impossible to make. And that frustration, that gap between what's possible in theory and what's practical, mirrors so much of what we grapple with in life. We come up with brilliant ideas, solutions that seem perfect on paper, only to run into obstacles we never anticipated, forcing us to reconsider everything from the ground up. Exotic matter represents that unknown hurdle, the thing that could unlock the wonders of the universe if only we could figure out how to make it work. When we talk about shortcuts through the universe, something deeper than physics emerges, something that touches on the very human desire to transcend limits. Imagine being able to bypass the immense distances that have always stood between us and the unknown, not through the cold detachment of equations and calculations, but through an experience that brings the stars closer. For millennia, the universe has been this vast, unreachable expanse, and now the idea of shortcuts rewrites that narrative. It isn't just about getting from one place to another faster. It's about experiencing the universe in a fundamentally different way. These shortcuts would make space not just a frontier, but a place we could traverse as easily as we do the roads on Earth. The human need to explore, to be part of something larger than ourselves, would finally have the means to stretch beyond imagination. What happens to us when the universe shrinks in this way? That grand scale that has always been beyond our reach becomes something we can hold in our hands. It changes not just our relationship with space, but with time and meaning. Right now, the sheer scale of the cosmos creates a sense of awe that humbles us, reminding us of our smallness in the grand scheme of things. But if we could take a shortcut through that scale, would we still feel the same way? Would standing on a distant planet feel as profound if getting there was as simple as stepping through a door? It challenges the very core of human experience, where distance has always carried a weight. In emotional depth, every journey requires effort, patience, and the sense of overcoming great odds. Shortcuts through the universe offer something new, yet in doing so, they strip away that traditional sense of adventure, of struggle that makes the destination worth reaching. At the same time, such a transformation brings a sense of closeness, a collapsing of barriers that have always defined our understanding of life beyond Earth. We've always been explorers, but the vastness of space has kept our exploring minds somewhat tethered to the familiar. Shortcuts, however, would shift this entirely. They would make the universe feel less like an untouchable mystery and more like an extension of home. The same instinct that makes us curious about what lies across the ocean would now drive us to reach out to other galaxies, to step onto distant moons as casually as we might visit another country. And in doing so, we would reshape our sense of identity, not as inhabitants of Earth, but as part of a much larger cosmic neighborhood. There's a subtle, almost philosophical transformation that happens here, too. The universe has always been defined by distance, by the separation between objects, between us and everything else. Take that distance away, and suddenly we are connected to everything in a way we've never experienced before. What does it mean to live in a universe where distance isn't a barrier? Where the journey doesn't require years of effort, but is instantaneous? We would become creatures no longer limited by physical boundaries, our reality no longer confined by the horizons we've always known. The sheer vastness of space, once something that filled us with awe and a bit of fear, would now be navigable, something we could explore in real time. But with that closeness comes a new kind of challenge. There's a weight that comes with realizing that the mysteries of the universe are no longer out of reach. The stars, once distant beacons of possibility, become part of everyday experience. It changes what we dream about, what we aspire to. There's always been a comfort in knowing that some things are beyond us, that we can imagine but never quite reach. It gives us something to strive for, something to wonder about in quiet moments. If we suddenly have access to all of it, what becomes of that dream? What happens when the universe is no longer a vast unknown, but a place we can visit whenever we wish? Does it diminish the mystery, the beauty, the sense of scale that has always shaped our understanding of our place in the cosmos? In a way, these shortcuts might make the universe feel smaller, more intimate, but they also present a profound opportunity. We wouldn't just be crossing physical distances. We would be crossing emotional and psychological thresholds, breaking down the walls that have kept us feeling isolated in a universe that has always seemed so indifferent to our existence. Suddenly, the cosmos isn't just a collection of distant stars and planets. It's a place we belong, a place we can touch and experience firsthand. And in that new reality, we might find new reasons to marvel at it all, not because of the vastness we can't reach, but because of the connections we can now make. The universe would no longer be a distant, abstract concept, but something deeply personal, an extension of our human curiosity, our desire to connect with the unknown. The human element in all of this is unavoidable. We've always pushed against the limits of what's possible, driven by the need to see what lies beyond. Shortcuts through the universe don't just fulfill that need. They redefine it, opening up possibilities we've barely begun to imagine. It isn't just about making space travel faster. It's about changing the way we think about space itself, the way we relate to the cosmos. And in doing so, we change ourselves, becoming part of a universe that, for the first time, feels as close as our own backyard. The idea of gateways to other universes is something that strikes a deep chord in the human imagination. It's not just about stepping into an entirely different world. It's about confronting the possibility that our reality is only one thread in a much larger fabric, one universe among countless others. The very thought of such gateways ignites something primal in us, a blend of fear, wonder, and curiosity. For as long as we've been aware of the universe, we've sought to understand it, to map its edges and find our place within it. But what if there are no edges? What if the universe we know is just one among many, each with its own rules, its own histories, its own truths? A gateway to another universe wouldn't just be a technological or scientific achievement. It would be a step into the unknown so profound that it would challenge the very essence of what it means to be human. For those who dare to walk through such a gateway, the experience wouldn't just be about exploration. It would be about leaving behind everything that defines our reality. Stepping into another universe means confronting the possibility that the laws of physics, the passage of time, even the concept of existence itself could be radically different. What would it feel like to exist in a universe where gravity doesn't behave the way it does here, where time flows in unpredictable ways, where life, if it exists at all, looks nothing like anything we've ever imagined? To cross that threshold is to accept that everything you know could be turned upside down, that you might never return the same, or even return at all. Yet, despite the unknowns, there's something irresistibly human about the idea of venturing through these gateways. Throughout history, we've always been driven by a need to go beyond, to see what lies on the other side, even when it's dangerous or impossible. Crossing into another universe would be the ultimate extension of that drive. It's about seeking more than answers. It's about understanding our place in a multiverse that we've only glimpsed in theory. The human heart, full of longing for discovery and connection, would push us toward these gateways, knowing that what lies beyond could forever change our understanding of reality, but unable to resist the pull of what could be found. There's also something deeply emotional about the notion of other universes. Our universe, vast as it is, can sometimes feel isolating. Even when we explore distant planets, the sheer scope of the cosmos makes us feel small, insignificant. But if there are other universes out there, connected by gateways, then perhaps we're not as alone as we think. Perhaps life exists in ways that are completely alien to us, yet still share the same basic desire for connection, for meaning. To step through a gateway is not just to explore. It's to search for a reflection of ourselves in the infinite, to see if there are echoes of our existence somewhere beyond the boundaries of our own reality. Of course, with such potential comes risk. Entering another universe could be dangerous in ways we can't even comprehend. A universe with different laws of physics could be hostile to life as we know it. Even if we survive the journey, we might find ourselves in an environment that our bodies and minds are ill-equipped to handle. Time itself could behave differently, leaving those who venture through a gateway stranded in a world where years pass in the blink of an eye or where minutes stretch into eternities. And yet, that risk is part of what makes the possibility so compelling. It's the very definition of a leap into the unknown, where the rewards could be immense, but the dangers equally so. There's also a philosophical dimension to consider. If we truly are able to step into other universes, what does that say about the nature of reality itself? We've always assumed that the universe we inhabit is all there is, but if there are other realities out there, connected by these gateways, then the very foundation of our existence becomes far more complex. It raises questions about fate, free will, and the nature of life itself. Are we just one version of an infinite number of possibilities? Are there other versions of ourselves living in these parallel universes, making different choices, following different paths? The idea of gateways to other universes doesn't just expand our understanding of space. It forces us to rethink everything we thought we knew about life, identity, and reality. In the end, the allure of these hypothetical gateways is not just about the science or the adventure. It's about the human need to push beyond the limits of the known, to confront the mysteries that lie just beyond the horizon. A gateway to another universe represents the ultimate unknown, a place where everything familiar could be stripped away, leaving us to confront the most fundamental questions about who we are and where we belong. And while the risks are great, the potential for discovery, for understanding something far greater than ourselves, is something we cannot help but reach for. Because, at our core, we are explorers, driven by the desire to know what lies beyond, even if it means stepping into a reality we can barely comprehend. The idea of a possible link between black holes and wormholes stirs something deep within us. It's as though, in the very nature of these cosmic mysteries, we find reflections of our own desire to connect distant, seemingly unreachable points. Black holes, with their immense gravitational pull, represent the ultimate end, a place where space and time collapse, where everything is drawn in and nothing escapes. But what if they're not just dead ends? What if, instead, black holes serve as gateways, the beginning of something else, a path to another part of the universe, or even another universe entirely? The connection between black holes and wormholes opens up possibilities that make us question our understanding of reality itself. We've always viewed black holes as destructive forces, places where anything that crosses the event horizon is lost forever. But wormholes, theoretically, offer a different kind of journey, one where space and time are bent in such a way that travel across unimaginable distances is not only possible but instantaneous. The human mind can't help but wonder if these two phenomena, both dealing with the warping of space-time, might be connected. It's the kind of question that keeps us up at night, imagining what it would mean if a black hole wasn't an end, but the entrance to a wormhole, a bridge to somewhere else. The mystery of black holes has always been their inaccessibility, their finality. But if wormholes are tied to them, then they become something else entirely, pathways to the unknown. For a long time, black holes have felt like a reminder of our limits, the places where even light itself can't escape. They are the ultimate boundaries of what we can explore. But wormholes suggest a way to cheat those boundaries. If black holes are connected to wormholes, then that boundary isn't as fixed as we once thought. Instead of an endless fall into oblivion, falling into a black hole could mean being flung across the universe, or perhaps even into another one altogether. It's a thrilling, yet terrifying thought, an experience that would completely change our understanding of space and time. And while we have no concrete evidence of this connection yet, the possibility alone is enough to capture the imagination. The connection between black holes and wormholes isn't just a theoretical curiosity. It taps into our very human need to believe that there are ways to traverse even the most insurmountable distances. It offers the hope that we might one day find shortcuts through the universe, not by bending the rules of physics, but by using the universe's own mechanisms. In a way, it's a comforting idea. Black holes, long thought of as the end of the road, could instead be part of something far more complex and hopeful. The terrifying finality of being swallowed by a black hole would give way to the possibility of emerging somewhere else, a new beginning rather than an end. This possibility also raises a deeply personal question about the nature of existence itself. If black holes and wormholes are connected, if they allow us to move through the universe in ways we can't yet fully comprehend, what does that mean for our own experience of reality? Do we really understand the nature of time, of space, of life? Or are we just scratching the surface? The idea of linking black holes and wormholes suggests that the universe might be more interconnected than we realize, that there are hidden paths and connections that we have yet to discover. It's a humbling thought, but also an inspiring one. The human desire to explore, to seek out the unknown, has always been driven by the hope that there is more to reality than what we can see or measure. This possible link between black holes and wormholes is a symbol of that hope, a tantalizing glimpse at something beyond our current understanding. There's also something deeply poetic about the idea. Black holes, the ultimate symbols of destruction, might actually be the key to creation. New worlds, new possibilities, new paths through the cosmos. Wormholes, by their nature, suggest connection, not isolation. They offer a way to bring distant points together, to make the unreachable reachable. And if black holes are connected to wormholes, then even the most extreme, destructive forces in the universe might have a hidden purpose, a function that allows for something far more incredible than we ever imagined. It's the kind of idea that speaks to a fundamental truth about human nature, that even in the face of darkness and the unknown, we search for meaning, for a way forward, for a connection to something larger than ourselves. If such a link exists, it would not only change our understanding of black holes and wormholes, but reshape our view of the universe itself. It would mean that the cosmos is filled with hidden routes and possibilities, that even the most daunting phenomena could lead to new discoveries. And it would remind us that the boundaries we see are often illusions, waiting to be broken through with enough curiosity, enough exploration, and enough daring to step into the unknown. The idea that something as mind-bending as a black hole or wormhole could exist in microscopic sizes stirs a completely different kind of wonder. It forces us to look at the universe not just in the grand, cosmic scale, but in the intricate, invisible layers that weave everything together. We tend to think of these phenomena as colossal, devouring stars or bending space in unimaginable ways. Yet the notion that they could also exist on a scale smaller than the eye can see changes the way we think about the very fabric of reality. What if, at the smallest levels, these cosmic structures are part of the unseen machinery that holds everything together? It's almost unsettling, the idea that something so powerful could be so small, quietly shaping the universe beneath our notice. If these microscopic versions of black holes or wormholes are real, they could be all around us, tucked into the spaces between atoms, within the structures that make up the fabric of matter itself. The thought of that is both humbling and strangely intimate. We are made of the same stuff as stars, and to imagine that the same forces capable of shaping galaxies could also exist within the tiniest particles of our bodies makes the universe feel closer, more connected. It's almost like discovering that the greatest mysteries of the cosmos aren't out there in the unreachable depths of space, but right here, part of the everyday world we touch and feel, hidden in plain sight. The human mind has always grappled with extremes, the vastness of space and the minuteness of the quantum world. And this idea ties them together in ways that stretch the imagination. To think that wormholes, with their potential to connect distant points in space, might also exist on a quantum scale, means that the universe operates with a complexity far beyond what we can grasp. It makes us reconsider what reality even is. If these miniature gateways or singularities exist, it could mean that the rules we thought applied to the large-scale universe also apply to the smallest structures of matter, only in ways we have yet to fully understand. The idea that there are entire realms of existence we're unaware of, simply because they're too small to detect, makes the universe seem like a vast, layered puzzle, with answers hidden in places we never thought to look. But beyond the science, there's something deeply human in this. The possibility of microscopic wormholes or black holes taps into our need to find connections, to understand how everything fits together. It makes us feel that perhaps the universe isn't just this chaotic, random expanse, but a structured, intricate web where everything, from the largest galaxy to the smallest particle, plays a role in the grand design. And if these microscopic structures exist, they're likely doing more than just sitting there. They could be influencing the way particles behave, the way matter forms, and even the way time itself moves. There's a certain beauty in that, in the thought that the universe's greatest mysteries are not confined to the distant reaches of space, but might also be unfolding at scales we can barely comprehend. For us, this idea feels like a mirror held up to our own sense of smallness. We are tiny beings in a vast cosmos, yet the idea of microscopic black holes and wormholes reminds us that even within the smallest spaces, entire universes of complexity might exist. It's a strange comfort to know that the vastness of the universe isn't just something out there, but is echoed in the smallest scales of reality too. It gives the sense that no matter how small or insignificant something might seem, it could be part of something much larger, much more important. In the same way, we might start to see ourselves, not as beings adrift in an overwhelming universe, but as part of that complexity, as small but essential pieces of a much larger whole. There's something oddly grounding about imagining black holes or wormholes in microscopic form. It makes the universe feel like less of a distant, untouchable entity and more like something we're intimately a part of. It also suggests that the key to understanding the grandest mysteries of existence might not lie in telescopes or space probes, but in microscopes, in the careful study of the smallest particles that make up everything we know. If these structures exist on that scale, then they could be the bridge between the quantum world and the cosmic, showing us that the two aren't as separate as we once thought. It's an invitation to look closer, to realize that the answers we seek in the stars might also be found within the atoms of our own bodies. The dream of faster-than-light travel isn't just about reaching far-off stars or exploring distant galaxies. It's about breaking free from the limitations that bind us. Time and space have always been the ultimate barriers, defining the limits of what we can achieve, how far we can go, and how much we can experience in a single lifetime. The thought of moving faster than light feels like the ultimate defiance against those constraints, like stepping beyond the edges of what we thought was possible and opening the door to a universe that becomes accessible not just in theory, but in reality. For humanity, it represents more than a technological challenge. It's a hope for freedom, for expanding our presence in the cosmos in ways that reshape our future. At its core, the idea of faster-than-light travel speaks to a deep-seated human longing to conquer distance, to shorten the immense gaps between us and the places we dream of going. It's not just about reaching the next star system or a distant planet. It's about collapsing the vastness of space into something manageable, something that no longer feels like a prison of time. We look up at the stars and see a universe that is full of potential, full of life and mysteries waiting to be uncovered. And yet the speed of light feels like an unbreakable chain that keeps us locked within our small corner of the cosmos. The possibility of faster-than-light travel is like the key to that chain, promising that one day, the entire universe could be within our reach, not in generations or millennia, but in the span of a single journey. What's fascinating about this concept is that it doesn't just challenge what we know about speed, it challenges our understanding of time itself. Traveling faster than light would mean not only outrunning the light that connects us to distant stars, but possibly manipulating time in ways we can barely imagine. In a sense, it would be like stepping outside the flow of time, bending it to our will rather than being bound by it. That idea alone feels almost magical, as if faster-than-light travel would be more than just a mode of transportation. It would be a way to experience time differently, to move through the universe in a way that defies the boundaries of both space and time. It would give us a sense of control over forces that, for all of human history, have seemed untouchable, and that's a deeply powerful idea. Yet, there's something personal about this dream, too. Faster-than-light travel is more than just a scientific or technological goal. It touches something emotional in us. It's about the connections we can't make right now. The people, the places, the possibilities that are out of reach simply because the universe is too vast and the speed of light too slow. Imagine what it would mean to travel not only to other star systems, but to do so in a way that allows us to maintain those connections, to explore without leaving everything we know behind forever. The distances between us, between planets, between stars, would no longer feel so overwhelming. We'd be able to venture out into the unknown and come back again, perhaps even in the same lifetime, bringing new knowledge, new experiences, and new stories. It's a kind of exploration that keeps humanity tied together, no matter how far we go. But beyond the excitement, there's an almost philosophical element to this potential. Moving faster than light would fundamentally change the way we see ourselves and our place in the universe. No longer confined to the slow crawl of light years, we would become beings capable of crossing the vast expanses of space with ease. That kind of transformation would force us to rethink what it means to exist within the universe. Are we limited creatures, bound by the laws of physics as we understand them now? Or is there something more to us, something that drives us to constantly push against those boundaries, to find ways around them, to discover the loopholes in the fabric of space and time? Faster-than-light travel is more than a physical challenge. It's a challenge to our imagination, to our sense of what's possible, and to the very nature of reality. The risks and challenges of such a journey are, of course, immense. The technology needed to achieve faster-than-light speeds doesn't exist yet, and even the theoretical frameworks are filled with uncertainties. There are questions about how to protect against the immense energy that would be required, the unknown effects of traveling at such speeds, and what happens to matter, or a human body, when it moves faster than the light that defines its position in space. But those challenges don't dampen the dream. They only make it more profound. The human spirit has always thrived on overcoming the impossible, on facing the vast unknown with a mixture of fear and determination. The thought of faster-than-light travel embodies that spirit. It's about daring to go further, to reach beyond the limits of what we know, and to find out what lies on the other side. In the end, the potential for faster-than-light travel isn't just about speed or distance. It's about changing our relationship with the universe itself. It's about moving from a place where the stars are distant, unreachable points of light to a future where they become destinations, places we can touch, explore, and understand. It's a dream that combines our most advanced scientific thinking with our most basic human desires. The need to connect, to explore, and to understand the world around us. And even though we may not be there yet, the mere possibility keeps the fire of curiosity and hope burning within us, driving us to find a way, no matter how difficult, to make that dream a reality. The influence of faster-than-light travel on causality and the potential for paradoxes is something that deeply unsettles the mind. Time has always been something we take for granted, moving forward in a steady, linear flow. Cause leads to effect, and the order of events is fundamental to how we understand everything from the smallest moments in life to the grandest movements of history. But what happens when faster-than-light travel comes into play? Suddenly, that comforting certainty begins to unravel. Moving faster than light might allow someone to arrive somewhere before they've even left, to experience a future before the present has had a chance to unfold. This twists our understanding of time, turning the very concept of cause and effect into something strange and uncertain. It opens the door to paradoxes that defy logic, situations where the natural order of events becomes tangled and confusing, where the past and future bleed into one another in ways that make us question reality itself. For us, living with the rhythm of time is as natural as breathing, and the idea of disrupting that flow feels almost wrong. If we could travel faster than light, it's not just that we'd be moving across space quickly, it's that we'd be bending time too. This raises a terrifying possibility. What if, in breaking through those limits, we also break causality itself? Imagine the consequences of arriving somewhere before the actions that should have led you there even occurred. How do you account for a future that comes before its cause, a result without a beginning? It's a mind-bending thought, one that makes us wonder if the very fabric of the universe would allow it. There's something unsettling about the idea that, in seeking to conquer the limits of speed and distance, we might accidentally unravel the logic that holds time together. The potential for paradoxes is even more disturbing. One of the most famous is the so-called grandfather paradox, where a person traveling through time might alter the past in such a way that their own existence becomes impossible. If faster-than-light travel enables not just movement through space, but also some form of time travel, then we're faced with the possibility of events looping back on themselves. What happens if you arrive at a destination before you ever set out? What if your actions there influence the reasons you set out in the first place? It becomes a loop with no clear beginning or end, where cause and effect blur together in ways that seem impossible to untangle. The implications of such paradoxes are more than just theoretical. They challenge the very way we experience existence. We like to think of time as something reliable, something that marches forward steadily. But if faster-than-light travel disrupts that, then the orderly progression of events might collapse into chaos. This introduces a kind of existential dread. We've always relied on time as a constant, as something that gives structure to our lives, our decisions, and our understanding of the universe. The idea that faster-than-light travel could break that structure feels deeply disorienting. It's not just that we wouldn't know what to expect. It's that we wouldn't be able to trust the basic flow of events anymore. How do you live in a universe where actions don't necessarily lead to predictable outcomes, where the future can interfere with the past, where paradoxes might arise that challenge the very nature of existence? It would be like living in a dream, where the normal rules don't apply and everything feels slightly off-kilter, yet it's real, affecting every moment of your life. There's a human element to this uncertainty too. We've always built our understanding of the world on the idea that actions have consequences. You make a decision, and it leads to a result. You follow a path, and it takes you somewhere. But if faster-than-light travel introduces paradoxes, it's as if that basic logic no longer holds. Suddenly, the comfort of knowing that what you do matters, that it shapes the future in a clear and consistent way, is stripped away. You might find yourself in a situation where your decisions lead to outcomes that loop back and affect the very reasons you made them. It's a disorienting thought, one that makes you question how much control we really have over our actions and their consequences. At the same time, there's something almost exhilarating about the idea of stepping outside the rigid boundaries of time. It taps into a part of us that longs for freedom, for a reality where we're not bound by the limitations of causality. Faster-than-light travel, with all its potential for paradoxes, feels like a key to breaking free from the constraints that have defined human existence since the beginning of time. It offers a glimpse of a universe where the old rules no longer apply, where we can explore not just the farthest reaches of space, but the boundaries of time itself. And yet, in doing so, it also presents a kind of danger. We've always assumed that time is a constant, but faster-than-light travel might reveal that it's far more fragile, far more complex than we've ever imagined. The influence on causality and the risk of paradoxes, then, is more than just a scientific puzzle. It's a challenge to our entire understanding of existence. It forces us to confront the possibility that the universe is far stranger and more unpredictable than we ever thought. And while the prospect of faster-than-light travel offers incredible potential, it also brings with it the risk of disrupting the very foundations of reality. It's a delicate balance, one that leaves us wondering whether, in our quest to conquer the stars, we might also open Pandora's box, unleashing forces that could forever change the way we experience time, space, and everything in between. The Einstein-Rosen bridge is one of those ideas that seems to exist at the intersection of science and imagination. It's the kind of concept that makes you question not just what's possible, but how reality itself might be constructed. On paper, it's a solution to the equations of general relativity, a theoretical bridge between two distant points in space-time, a tunnel that could connect regions of the universe that might otherwise be unreachable. But it's more than just math. It's a glimpse into a universe where the distances between stars and galaxies might not be the impassable gulfs we once thought them to be. It stirs something deeply human in us, this notion that there could be shortcuts through space, hidden paths woven into the fabric of reality itself, waiting to be discovered. For many, the Einstein-Rosen bridge is something of a cosmic escape hatch, a way to bypass the limitations of space and time. We've always been fascinated by the idea of traveling vast distances in an instant, and the bridge promises just that. It offers the tantalizing possibility of moving between different parts of the universe without having to endure the endless stretch of time that comes with light-speed travel. The idea that two distant points could be connected as easily as stepping through a doorway feels like an answer to one of our oldest longings: the desire to explore the universe without being bound by its vastness. We're drawn to the idea because, at its heart, it's about overcoming the isolation of distance, making the unreachable seem suddenly close, almost intimate. But as compelling as it is, the Einstein-Rosen bridge isn't without its challenges. It's not just a matter of opening the door and walking through. The bridge itself, theoretically, is incredibly unstable. The forces at play within it are so immense that they could collapse almost instantly, making any journey through it both perilous and uncertain. The bridge might be there, but it's fragile, like a tightrope stretched across a chasm, and the slightest disturbance could cause it to fall apart. It's a reminder that, even as we dream of conquering the cosmos, the universe doesn't yield its secrets easily. We might find ways to create or discover these bridges, but the journey through them would require facing dangers we can barely imagine. And then there's the matter of where these bridges might lead. The idea of an Einstein-Rosen bridge isn't just about traveling across the universe. It could also connect to different parts of space-time, or even to entirely different universes. The possibility that stepping through such a bridge might take you not just to another star, but to another reality, raises all kinds of philosophical and existential questions. What if, on the other side, the laws of physics were different? What if time moved in strange, unpredictable ways? It's not just a shortcut through space. It could be a doorway to places where the very nature of existence is unfamiliar. That thought is thrilling, but also deeply unsettling. We might find ourselves in a universe where everything we know is upended, where the rules we've lived by no longer apply. For us, the Einstein-Rosen bridge feels like a metaphor for possibility, but also for the limits of our understanding. It shows us that the universe might be far more connected than we realize, with hidden pathways linking places we never thought could touch. But it also reminds us that those connections come with risks, with the possibility of stepping into the unknown and finding that it's not as welcoming as we'd hoped. It's the kind of idea that forces us to think carefully about what we're willing to risk in our quest for discovery. Do we venture through, knowing that the bridge could collapse behind us, leaving us stranded? Do we take the chance that we might emerge somewhere familiar, or in a place that feels like an entirely different reality? There's something deeply human in the way the Einstein-Rosen bridge captures both our desire for exploration and our fear of the unknown. It's the kind of concept that both inspires and humbles us, making us aware of just how little we truly understand about the universe we live in. On one hand, it offers hope. The possibility that we're not as isolated in the cosmos as we once thought, that there are ways to traverse the vast distances that separate us from other stars, other galaxies, other worlds. On the other hand, it forces us to confront the fact that those ways might be fraught with danger, with the kinds of risks that could easily lead to disaster if we're not careful. Ultimately, the Einstein-Rosen bridge is a reminder that the universe is full of mysteries we've only just begun to explore. It teases us with the idea that space and time aren't the rigid, unchanging things they seem to be, but are instead part of a dynamic, interconnected web that we're only now starting to understand. The bridge might be a mathematical abstraction, something that exists only on paper for now, but the fact that it's even a possibility speaks to the incredible complexity of the universe we inhabit. It's a glimpse of a future where the boundaries of space and time are no longer limits, but opportunities, where the vast distances that once seemed so daunting might be crossed with the right understanding, the right technology, and the right courage. Time dilation in wormholes presents one of the most mind-bending aspects of what it means to experience time. We're used to the idea of time moving at a constant rate, every second ticking by in perfect rhythm, whether we're sitting at home or traveling across the world. But the deeper you dive into the world of wormholes, the more that comforting sense of predictability slips away. Wormholes, with their strange geometry and connection to the fabric of space-time, don't just play with the idea of distance. They also warp time itself. In this bending and twisting of reality, time can pass very differently depending on where you are, creating the kind of situation where someone could experience just a few minutes while, for someone else far away or even back home, years could have gone by. This disconnect between the familiar and the strange leaves you grappling with how deeply connected space and time truly are. The idea of time dilation is rooted in the fact that gravity has the power to stretch and compress time. And wormholes, being these extreme entities with immense gravitational forces at play, take this to another level. Imagine traveling through a wormhole. On your journey, as you move closer to the wormhole's throat, you might not notice anything strange at first. Time, for you, would seem to pass as it always has. But to an observer watching from a distance, it would be a different story. They might see you moving slower and slower, as though you were frozen in place, hanging on the edge of the wormhole, while time for them continued to tick on normally. For the traveler, a short journey through the wormhole could feel like a few moments, but when they emerge, they might find that entire lifetimes have passed on the outside. It's a jarring thought that while you experience just an instant, everything you once knew might have already faded into history. What makes this concept hit even harder is the realization that time dilation isn't just a trick of perspective. It's not an illusion. The time you experience within the wormhole is genuinely different from the time experienced outside it. This creates a powerful sense of disconnection. If you were to travel through a wormhole, you might find yourself confronting a future you didn't expect, one where the people you knew are older, perhaps even gone, where the world has moved on without you. It's not just a question of space, but of time slipping out of sync. This is a deeply unsettling aspect of wormhole travel because it pulls at something fundamental in the human experience. The sense that we're moving forward through time together with those around us. Time dilation disrupts that bond, leaving you out of step with the world you left behind. For those who've lived their lives bound by the rhythms of Earth, where every moment feels shared with others, the prospect of time warping in a wormhole is both a marvel and a terror. On one hand, it offers the possibility of reaching places that would otherwise be out of our grasp, allowing us to travel unimaginable distances in what feels like no time at all. On the other hand, it introduces a kind of loneliness, the idea that while you journey across the stars, the universe you knew is slipping away from you, lost in the accelerating flow of time. To cross a wormhole and look back at everything you knew, only to see it far removed, changed by the march of time that didn't touch you in the same way, would be an isolating and profound experience. It's not just about reaching new places, it's about losing touch with the ones you came from. Time dilation in wormholes also makes you question what it means to live in a universe where time isn't the same for everyone. When we imagine the future, it's usually with the expectation that we'll experience it together. Yet, through the lens of time dilation, we might realize that time isn't a shared journey but something that stretches and bends according to where we are in the cosmos. It's a humbling realization, one that makes us aware of how small we are in the grand scheme of things, and how the universe operates on scales that are both alien and indifferent to our human sense of time. The idea that time might flow faster for someone standing still on a distant planet, while barely moving for someone traveling through a wormhole, doesn't just challenge our sense of logic. It challenges our emotional connection to time itself. The emotional weight of time dilation in wormholes lies in the fact that it plays with something so deeply embedded in the human experience: the passage of time itself. We structure our lives around time: birthdays, seasons, the aging of those we love. Time defines our memories and our future hopes. To encounter a phenomenon where time becomes flexible, unpredictable, and unshared is to face a reality that could tear at the very core of what makes us human. How would it feel to return from a journey through a wormhole to find the world transformed by the passage of years, or even centuries, while for you, only moments had passed? It's not just a question of physics, but of heartache, of the slow realization that while you've traveled, the people you once knew have grown older or faded into the past. It's in these emotional gaps where the human story of wormhole travel really unfolds. The physics of time dilation is fascinating, but it's the emotional consequences that would resonate most deeply. If wormholes ever become a reality, the travelers passing through them might not just be voyagers into new realms of space. They might also be explorers of the future, stepping into a world that has already moved on without them. Time dilation isn't just a technical quirk of wormholes. It's the reminder that, in seeking to conquer the vast distances of the universe, we might also have to confront the reality that time, once so familiar, can become something alien and unrecognizable. It's the price of pushing the boundaries of what's possible, a price that is paid not in distance, but in time. Imagine for a moment, standing on the edge of something that defies every intuitive understanding of space. A passageway of sorts, one that doesn't just stretch across our universe, but bends it, warps it in such a way that the path you'd normally have to traverse, billions of light years, becomes no more than a simple step. This is what a traversible wormhole promises: a doorway not only through the vastness of space, but possibly even through the flow of time itself. But unlike the violent, uninhabitable maelstrom we might associate with black holes, a traversible wormhole suggests something more approachable, more stable, something that could be crossed without being crushed or torn apart. To create a wormhole that is safe for travel, you'd need to engineer it with care, in ways that boggle the mind. Exotic matter is the key, material that has negative energy density, acting almost like an invisible scaffold holding the wormhole open, defying the natural inclination for it to collapse under its own gravity. Without this, even the slightest disturbance could send the walls of the wormhole crashing inwards, cutting off the path between the 2 points of space and potentially trapping anything, or anyone, inside. There's a delicate balance at play, almost like a suspension bridge across a deep chasm. It needs constant tension, and without it, the structure would be no more than an impossible dream. The allure of traversible wormholes isn't just in their existence, but in the possibilities they present. Imagine being able to reach another star system not in centuries or millennia, but in minutes, time and space folding in on themselves, bringing distant worlds into the palm of your hand. The experience would be surreal, as if reality itself had bent to your will, offering up the most profound shortcut ever conceived. Yet, the journey through such a wormhole would likely bring its own strangeness. Space and time might behave in unfamiliar ways, the very fabric of reality stretching and warping around you. The sense of disconnection from the universe, as you know it, could be both thrilling and disorienting, a moment where the laws of nature seem to hold their breath. And then there's the question of where such a journey might take you. Beyond familiar stars, beyond galaxies we've mapped, there's a tantalizing thought. Could some of these wormholes serve as bridges not just between locations in our universe, but to entirely different universes? Parallel realities, perhaps ones with different laws of physics, where the rules we take for granted no longer apply. The thought that stepping into a traversible wormhole could take you into a reality that is fundamentally unlike anything you've ever known, that alone is enough to stir a sense of wonder and trepidation. You wouldn't just be traveling through space. You'd be exploring the boundaries of existence itself. But the physics behind this dream remains frustratingly elusive. While the mathematics suggest that such traversible wormholes are possible, the actual building blocks, the exotic matter needed, have yet to be found. It's a curious limbo, knowing that such wonders could be theoretically real, while standing on the edge of our knowledge, with no concrete way to bring them into existence. Yet, that doesn't stop us from dreaming, from imagining what it would feel like to step through that doorway and emerge in a place where the universe is both familiar and utterly strange, all at once. There's something almost unsettling about the idea of exotic matter, something that seems to slip away from our everyday understanding of the universe. When we think of matter, we imagine the stuff we can touch and feel, the solidity of a rock, the air we breathe, the warmth of a flame. But exotic matter stands apart from all of that. It doesn't behave in any way we're accustomed to. It's as if it exists on the fringe of reality, bending the rules that we've come to rely on. And then there's the concept of negative energy. It's not like the energy of a gust of wind or the charge flowing through a wire. Instead, it's something that feels counterintuitive, almost contradictory. It's energy, but less than nothing. A vacuum in the fabric of space that can push and pull in ways we're only beginning to comprehend. If you were to encounter exotic matter, it wouldn't feel like anything familiar. It might even be disturbing. Not cold or hot, not heavy or light, but somehow off, as if reality around it is skewed. This material, if it exists, isn't just another form of matter. It's the key to holding open a wormhole, a way to resist the gravitational forces that would normally cause it to snap shut. Without exotic matter, a wormhole would collapse almost instantly, closing off the passage and making any travel through it impossible. But exotic matter, with its strange properties, keeps the walls of the wormhole stretched apart, allowing it to remain stable long enough for something to pass through. Negative energy, on the other hand, is like the dark twin of what we know as energy. It's not just the absence of energy, but a force in its own right, one that can bend space-time in the opposite direction from what gravity normally does. Where gravity pulls, negative energy can push, almost as though it's working to create a balance in the universe's equations. But the real challenge isn't just imagining it. It's finding a way to generate it, to harness it. So far, we've only glimpsed the tiniest hints of negative energy in experiments, like those involving quantum fields. It appears in fleeting moments, almost like a shadow cast by reality itself. The trick would be finding a way to control it, to produce it on a scale large enough to make a difference. And what a difference it would make. With exotic matter and negative energy, we'd be bending space-time to our will, reshaping the very fabric of the universe. These concepts aren't just abstract theories. They represent a kind of power that could open up entirely new ways of traveling through space, of interacting with the cosmos. Yet, they remain elusive, out of reach, as if the universe is keeping them just beyond our fingertips. It's frustrating but also inspiring. We know the potential is there, just waiting to be unlocked, waiting for us to discover how to tap into the hidden forces that could make the impossible possible. There's a strange beauty in it, the idea that the universe holds these secrets, and it's up to us to uncover them, step by step. In the world of quantum physics, the rules become unpredictable, almost whimsical, as if the universe itself is playing a game we don't fully understand. Wormholes, in this realm, aren't the vast cosmic tunnels you might envision in deep space. Instead, they could exist on the smallest possible scales, within the fabric of the universe itself, where particles pop in and out of existence in a constant, chaotic dance. In this quantum soup, the idea of wormholes takes on a different, more elusive form. They may appear and disappear in a flash, connecting different points of space and time for the briefest moments before vanishing again, almost like a ripple on the surface of a pond, too small and fleeting for us to detect directly. There's something profoundly strange about this idea, that space itself, at its most fundamental level, is riddled with these tiny, ephemeral connections. If you could somehow zoom in far enough, past atoms and subatomic particles, past the quantum foam where uncertainty reigns supreme, you might catch a glimpse of these miniature wormholes. But their fleeting nature makes them almost like a whisper in the background noise of the universe, impossible to pin down, let alone control. Yet, in their existence lies a tantalizing possibility. If quantum physics allows for these tiny wormholes, could they be scaled up, made stable and large enough for something more significant, like information or even matter, to pass through? Quantum entanglement adds another layer to this mystery. Particles, when entangled, share a connection that defies our classical understanding of space and distance. No matter how far apart they are, they seem to communicate instantly, as if space between them doesn't matter. Some theories suggest that this entanglement might be linked to microscopic wormholes, as if these particles are connected by a thread, a hidden bridge that defies the normal constraints of the universe. It's a mind-bending thought that what we see as quantum behavior could actually be tiny wormholes in action, weaving the fabric of reality together in ways we can't fully grasp. If that's the case, then wormholes aren't just theoretical constructs. They could be an intrinsic part of how the universe operates at its most fundamental level. Yet, the challenge lies in the fact that, in the quantum world, everything is governed by uncertainty. The very act of observing or measuring something changes it. So, trying to study or manipulate these potential wormholes would be like trying to catch smoke with your bare hands. The closer you get, the more elusive they become. But this doesn't make the pursuit any less important. In fact, it's what drives physicists forward. The idea that somewhere in the strange dance of quantum mechanics, there might be a way to unlock the secrets of wormholes, to understand how they work and, perhaps one day, use them in ways we can't yet imagine. For now, though, they remain part of the mysterious undercurrent of quantum physics, a hint of something bigger, waiting to be discovered. The universe is whispering to us through these tiny anomalies, daring us to dive deeper, to unravel the riddles that lie at the intersection of space, time, and the quantum world. It's a reminder that even in the smallest corners of reality, there are still vast mysteries to explore, and wormholes may be one of the strangest and most intriguing among them. The idea of black holes and wormholes stirs something deep within us. Two cosmic phenomena that stretch the limits of our understanding, yet couldn't be more different in what they represent. Black holes, for all their mystery, evoke a sense of finality. They are places where time and space converge into a singularity, where everything is pulled inward and nothing escapes. Falling into a black hole feels like the ultimate end, a one-way ticket to nowhere, where even light itself cannot break free from its gravitational grip. It's as if the universe has drawn a line around these regions, and anything that crosses it is lost forever. There's something profoundly unsettling about this, a reminder of nature's raw, untamed power. Wormholes, on the other hand, evoke the opposite feeling. They represent not an end, but a possibility, a chance to traverse space and time in ways that defy the conventional. Where black holes seem to trap, wormholes promise escape. They could connect distant parts of the universe or even serve as shortcuts to other dimensions or times. A wormhole feels like an invitation to explore, to venture into the unknown, and perhaps return with knowledge of a reality beyond our own. But unlike black holes, which we know exist and can observe from a distance, wormholes remain more elusive, hanging in the balance between theory and reality, a tantalizing idea that hasn't yet crossed into the realm of certainty. What's fascinating is that black holes and wormholes might not be entirely separate from one another. Some theories suggest that a wormhole could exist at the heart of a black hole, hidden beneath the event horizon where all known physics begins to break down. If true, this would mean that, rather than falling into oblivion, one might be slipping through a cosmic doorway. Yet, the dangers of such a journey can't be understated. A black hole's immense gravity would tear apart anything approaching it, shredding matter down to its atomic structure in what's known as spaghettification. a violent and irreversible fate. To survive, the wormhole would need to remain stable and avoid the destructive forces of the black hole singularity, an almost impossible feat given our current understanding of physics. In their own way, both black holes and wormholes challenge the limits of our perception. One is real, tangible, something we've seen through the eyes of telescopes as it bends light and consumes entire stars. The other is still a mystery, something imagined in equations and theories, waiting to be proven. Yet, both capture the same sense of wonder. The notion that the universe is far stranger and more complex than we could ever fully grasp. Standing on the edge of either would feel like looking into the unknown, but with entirely different emotions. With a black hole, you'd feel the weight of inevitability, a force pulling you in that cannot be resisted. With a wormhole, you might feel the thrill of possibility, the sense that you could step into another reality entirely and come out the other side changed in ways you can't yet understand. Ultimately, black holes and wormholes are reflections of two sides of the same cosmic coin. One a symbol of endings, the other of new beginnings. Both hold secrets about the nature of the universe, about the way space, time, and gravity interact on scales we can barely comprehend. And while black holes loom large in the observable universe, reminding us of the limits of what we can know, wormholes remain a doorway yet to be opened, inviting us to imagine a future where the boundaries of time and space are no longer fixed, but fluid, shaped by our ability to explore and understand them. The thought of wormholes and time travel stirs something deep, a sense of both excitement and unease. On the one hand, the idea of slipping through a wormhole and stepping into a different time seems like the ultimate fantasy, to witness history firsthand, or perhaps even rewrite it. But on the other hand, it brings with it a profound sense of danger, because messing with time means confronting paradoxes that challenge the very nature of cause and effect. It's like playing a game with the universe where the rules aren't fully understood, and the stakes are impossibly high. Imagine walking through a wormhole and finding yourself decades in the past. Maybe you make a small change, save someone's life, prevent a disaster, and suddenly, the future you came from no longer exists. You've set off a chain reaction, unraveling the timeline you once knew. This is the essence of the grandfather paradox, one of the most famous puzzles in time travel. If you were to go back and accidentally prevent your own grandparents from meeting, how could you have ever been born to travel back in time in the first place? The paradox traps you in a loop of contradictions, where your actions in the past ripple forward, altering the present in ways that erase the very circumstances that made those actions possible. Wormholes, by their nature, could allow these kinds of temporal shortcuts, connecting not only distant points in space but also different points in time. But here's where the real challenge lies. The universe doesn't seem to like paradoxes. Some theories suggest that even if you could travel back in time through a wormhole, the universe would find a way to prevent you from causing a contradiction. Maybe you'd be unable to make any meaningful changes, no matter how hard you tried. The so-called self-consistency principle suggests that events would conspire to keep the timeline intact. You might get close to changing history, but something would always intervene. A missed opportunity, a forgotten detail, a twist of fate. The universe, in this view, protects itself from paradoxes like a cosmic safety net. But what if the universe is more flexible than we think? Another possibility is that time travel through wormholes could create entirely new timelines, alternate realities that splinter off from the moment a paradox occurs. In this scenario, your actions in the past wouldn't destroy your original timeline, but would instead spawn a new one where the changes you made play out. It's a strange and unsettling idea that every decision, every action, could create a branching path, leading to countless alternate versions of reality. In one timeline, you were never born. In another, you live a life completely different from the one you remember. It raises the question of what real even means when there are potentially infinite versions of you scattered across the multiverse, each living out a different possibility. There's something profoundly human in all of this. Our deep desire to understand and control the passage of time, to rewrite the parts of our lives we regret, to explore the what-ifs of our choices. Wormholes offer a tantalizing glimpse of what might be possible, but they also force us to confront the limitations of our understanding. Time isn't just a line to be followed. It's a delicate web where each thread is connected to every other. Tugging on one part could ripple across the whole, with consequences we can't predict or control. The paradoxes of time travel aren't just puzzles for physicists. They are reflections of our deepest fears and desires, our longing to reshape the past while grappling with the knowledge that some things may be better left untouched. So even as we dream of wormholes and the possibilities they hold, we're reminded of the fragility of time and the careful balance that exists between the past, present, and future. Crossing that boundary, no matter how tempting, would be a journey fraught with complexities that stretch far beyond the physics involved. It's a dance with fate, where every step could lead to an outcome we might not be ready for. And yet, the temptation remains to peer into the unknown, to see what lies on the other side of time itself. Hawking radiation feels like a whisper from the edge of a black hole, a reminder that even the most powerful forces in the universe aren't entirely invincible. It's strange, really. The idea that something as dense, as inescapable as a black hole could slowly evaporate, releasing particles into the void over unimaginable stretches of time. This radiation, named after Stephen Hawking, arises from the bizarre interplay of quantum mechanics and gravity, a fleeting burst of energy created when virtual particles, pairs that blink into existence at the edge of the event horizon, are split apart. One particle gets swallowed, while the other escapes, carrying away just the tiniest fraction of the black hole's mass. Over time, this slow leak adds up, and in the distant future, even the most massive black holes could dwindle to nothing, vanishing in a final burst of energy. The connection to wormholes is subtle, but it's there. Hawking radiation forces us to rethink the permanence of these cosmic phenomena. Just as black holes can shrink, losing energy to the vastness of space, wormholes, if they exist, might not be as stable as we hope. The same quantum effects that cause Hawking radiation could, in theory, affect the delicate balance of a wormhole. If particles at the edge of a black hole can escape, what's to stop a wormhole from experiencing similar quantum fluctuations? It makes you wonder whether wormholes, too, might slowly unravel, losing their structure to the relentless forces of quantum physics, no matter how well we engineer them. There's something humbling about the thought. Here we are, imagining wormholes as gateways to distant realms, shortcuts through space and time. And yet the very quantum forces that give us hope of creating these portals may also be the ones that ultimately undermine them. Hawking radiation serves as a reminder that nothing, not even the most fantastical creations of our imagination, is immune to the deeper laws of the universe. It's a lesson in fragility, that even as we dream of bending space-time, the universe has its own way of reasserting control, its own way of making sure the balance is maintained. And yet, it's not just a limitation, it's also a possibility. Hawking radiation has shown us that black holes aren't the eternal prisons we once thought they were. They can leak energy, they can change. If wormholes can be similarly influenced by quantum mechanics, perhaps there's a way to harness that process, to manipulate it, even stabilize it. The idea that wormholes could be affected by Hawking-like radiation doesn't close the door on them. It might actually open up new ways of thinking about how to keep them open, to prevent them from collapsing under the weight of quantum uncertainty. Hawking radiation is, in its essence, a glimpse into the hidden workings of the universe. It's a phenomenon that seems impossibly small and insignificant, tiny particles escaping from the edge of a black hole. Yet it holds profound implications for our understanding of space, time, and everything in between. When we think about wormholes, we can't ignore this effect. The same quantum dance that causes black holes to lose mass over eons might also play a role in shaping the future of wormholes. It's a delicate balance between possibility and decay, between the dream of cosmic shortcuts and the reality of quantum physics' relentless pull. In the end, Hawking radiation and wormholes are both reminders that the universe is full of contradictions, full of mysteries that refuse to yield easily to our understanding. But they also show us that even in the most extreme environments, there is room for change, for transformation. Wormholes might not be as stable as we wish, but that doesn't mean the journey to understand them ends there. It's just the beginning of a deeper, more nuanced exploration of the cosmos, one that embraces both the wonder and the complexity of the universe in all its strange, quantum-driven beauty. There's something inherently human about the desire to believe in more than one version of reality, to imagine that somewhere, in a universe just out of reach, things could have unfolded differently. Multiverse theories play directly into that longing, offering the possibility that every choice, every moment, might spin off into its own separate universe. It's a comforting thought in a way, suggesting that somewhere out there, different versions of us might exist. Versions that made different decisions, avoided mistakes, or found paths we never quite saw in this world. But these theories aren't just philosophical musings. They're rooted in some of the most mind-bending ideas in physics, and wormholes might just be the threads that weave these different realities together. Wormholes, if they exist, could serve as bridges between not just distant points in our own universe, but entirely different universes as well. The notion that a tunnel could connect our reality to another, perhaps with different physical laws, different constants, is staggering. Imagine stepping through a wormhole and finding yourself in a universe where time flows backward, or where gravity works in reverse, or where the stars themselves burn a different color. Each universe could represent a different version of reality, some only slightly altered from our own, others completely unrecognizable. The multiverse, in this view, becomes not just a collection of abstract ideas but a vast, interconnected web of possibilities, with wormholes serving as the hidden passages that link them together. But the thought of crossing between universes through a wormhole brings a mix of awe and apprehension. If wormholes allow us to jump between different realities, then the consequences could be profound and unpredictable. What happens if you cross over into a universe where your very existence creates a paradox? Or if the universe you enter is unstable, collapsing the moment you step through? The idea of traveling between universes forces us to confront the unknown in a way that feels both thrilling and terrifying. You could encounter a version of reality so foreign that even the basic rules of nature don't apply, leaving you stranded in a place that defies all understanding. Yet, the allure of the multiverse is impossible to ignore. The idea that wormholes might connect different universes opens up a new realm of exploration, one where the possibilities seem endless. Maybe you'd find universes that feel eerily familiar, places where history played out just a little differently, where events unfolded in ways that reflect what might have been. Or perhaps you'd stumble upon universes where life as we know it couldn't exist, where the conditions are so radically different that the mere act of stepping through could be life-threatening. Every wormhole could lead to a new chapter, a new possibility, a glimpse into a reality that offers answers, or questions we hadn't even thought to ask. But alongside the wonder of multiverse theories lies a sobering truth. If wormholes truly connect different universes, then we might never fully grasp the implications of what we discover. The sheer variety of realities could be overwhelming, and the laws that govern one universe might be completely irrelevant in another. It's as though each step through a wormhole brings not just a new world, but a new set of rules, a new framework for understanding existence itself. The multiverse, with all its infinite possibilities, is both a gift and a challenge, a promise of endless discovery, but also a reminder of how small and fleeting our understanding of the cosmos truly is. In the end, the connection between wormholes and the multiverse touches on something deeply personal. It's not just about physics or theoretical models. It's about the human desire to explore, to understand, to push the boundaries of what's possible. Wormholes, if they allow us to peer into different universes, would be the ultimate frontier, a way to not only traverse space and time, but to touch the very fabric of reality itself. And as we contemplate what lies beyond, we're reminded that the universe, or rather the multiverse, is far stranger, far more expansive than we could ever have imagined. Yet, for all its strangeness, it remains a source of endless fascination, calling us to step through the wormhole and see what waits on the other side. The idea of stepping through a wormhole carries an undeniable sense of adventure, but beneath that excitement is a stark reality. These shortcuts through space-time are far from stable. Stability, in the context of wormholes, becomes the greatest hurdle. The structure of a wormhole is a fragile, delicate thing, held together by forces that are constantly trying to collapse it. At first glance, the possibility of a tunnel through the fabric of the universe sounds like science fiction, but the deeper you look into it, the more it feels like walking a tightrope where a single misstep can unravel everything. For a wormhole to remain open, it requires something beyond what we know in everyday experience. The forces that govern normal matter simply don't apply here. Left to its own devices, a wormhole would pinch off almost as soon as it forms, crushed by the overwhelming force of gravity that pulls everything toward closure. It's like trying to keep a house of cards standing in a windstorm. Every element is working against its survival. To keep this tunnel open, to stop it from collapsing under its own weight, physicists theorize that something exotic is required. This exotic matter wouldn't behave like anything we're familiar with. It would need to have negative energy, a force that could push back against gravity, acting like an invisible scaffolding that holds the walls of the wormhole apart. Even with such strange material, the question of stability remains tenuous at best. Negative energy is not something we can easily create or control, and it may not even exist in quantities large enough to support a traversible wormhole. Theoretical physics suggests it's possible, but possible in the way that balancing on the edge of a razor is possible. Any disturbance, any shift in the balance, could cause the wormhole to collapse, trapping anything inside or worse, ripping it apart as the tunnel caves in. The risks are real, and they highlight just how precarious these hypothetical constructs are. It's not simply a matter of opening a wormhole and stepping through. It's about maintaining it in the face of forces that are constantly trying to tear it down. It's hard not to think of wormholes as fleeting, temporary things, as fragile as soap bubbles on the surface of a pond. Their existence, even if proven, would depend on such delicate conditions that the slightest disruption could end them. Cosmic rays, tiny fluctuations in the energy fields that surround us, or even the act of passing through could destabilize the entire structure. It's a sobering reminder that the universe doesn't bend easily to our will. These fantastical ideas come with their own limitations, their own set of rules that we can't ignore. In chasing after the dream of wormholes, we're also forced to reckon with their instability, a constant tension between what's possible and what's likely to fall apart. There's a human element to all of this, though, in the way we continue to push the boundaries despite the fragility of it all. The prospect of instability doesn't stop us from dreaming. It's the way we've always approached the unknown, knowing that there's risk, knowing that what we seek may be fragile and impermanent, yet still reaching for it. Wormholes, in their unstable, fleeting existence, reflect that same drive. They may collapse under the weight of the universe's forces, but the fact that we even entertain the possibility of stabilizing them speaks to the audacity of human imagination. We understand the risks, we recognize the fragility, and yet we press on, daring to hold the universe open, if only for a moment, to see what lies on the other side. Cosmic strings are like threads of a forgotten universe, remnants from the earliest moments after the Big Bang, when the cosmos was still young and raw. These infinitely thin but immensely dense strands of energy are theorized to stretch across the universe, cutting through space-time with a force that's almost impossible to comprehend. Imagine a thread of pure energy, a relic from when the universe was still forming, that holds within it the tension of creation itself. It's a mind-bending idea, but cosmic strings carry with them a deeper mystery, the potential to interact with wormholes in ways we can only begin to speculate. Wormholes, already fragile and teetering on the edge of existence, might find stability in the presence of these cosmic strings. It's as if these threads, relics of the universe's infancy, could be used as anchors, holding open the walls of a wormhole and preventing them from collapsing. The tension within a cosmic string is immense, so much so that it could warp space-time, bending it in ways that are difficult to imagine. If a wormhole were to intersect with a cosmic string, the energy from the string could act as a stabilizing force, preventing the wormhole from pinching shut under the crushing pull of gravity. In a sense, the cosmic string becomes a lifeline for the wormhole, a way to hold the passage open long enough to traverse it. There's something poetic about the idea. These ancient strings, older than galaxies, could be the key to unlocking wormholes, connecting distant parts of the universe, or even bridging different universes altogether. Cosmic strings, born in the fire of the universe's creation, would serve as the foundation for something entirely new. Yet, as with anything in the universe, there's a tension between the potential and the peril. The energy stored within a cosmic string is immense, and if something were to go wrong, the release of that energy could have catastrophic consequences. A misalignment, a miscalculation, and the string could tear through the wormhole, shredding space-time and everything caught within. This delicate balance between creation and destruction, between holding a wormhole open and the risk of collapse, speaks to the precarious nature of the universe itself. Cosmic strings, if they exist, are incredibly rare, and finding one, let alone using it to stabilize a wormhole, would be an astronomical challenge. But the possibility is tantalizing. If we could harness the power of cosmic strings, we might unlock a method for not just traveling through space, but bending the very fabric of the cosmos to our will. It's a vision of the future that feels both awe-inspiring and humbling, a reminder of how little we truly understand about the universe we live in. Yet, there's a human element to all this theorizing. The idea that we could take something so ancient, so fundamental, and use it to open doorways to distant parts of the universe or to other universes entirely. It's a reflection of our deepest instincts to explore, to discover. Cosmic strings and wormholes represent the ultimate expression of curiosity, the drive to not only understand the universe but to bend it in ways that allow us to transcend the limitations of distance and time. It's the same drive that's always pushed us forward, from the first humans who looked up at the stars and wondered what lay beyond the horizon to the scientists today who speculate about the nature of space-time itself. In the end, cosmic strings and wormholes are more than just theoretical constructs. They represent the intersection of the past and the future, the ancient and the new, bound together by the mysteries of space-time. They are reminders of the power and fragility of the universe, of how the smallest threads of energy could hold the key to the most profound journeys we might ever undertake. And as we ponder the possibilities, we're left with the understanding that even the most complex, untouchable ideas have roots in the same curiosity that's always driven us, the desire to reach beyond the known and touch the very edge of existence. Wormholes have always captured the human imagination, especially in science fiction, where they serve as gateways to limitless adventure. They offer a way to sidestep the vastness of space and time, allowing characters to traverse galaxies in the blink of an eye, bypassing the usual constraints of distance and technology. There's something deeply relatable about this concept, the idea that with the right kind of passage, we could escape the slow crawl of reality and leap straight into the unknown. Science fiction has long used wormholes as a narrative device to not just connect distant worlds, but to explore the boundaries of what we understand and what we can only dream about. In the realm of fiction, wormholes become the ultimate key to unlocking distant realms. They're portrayed as shimmering portals or rippling distortions in the fabric of space-time, often sitting at the edge of discovery, just waiting to be crossed. Characters stand on the precipice of these strange phenomena, filled with a mix of fear and wonder, not knowing what awaits them on the other side. These wormholes are more than just tools for travel. They're symbols of mystery, representing the tension between the known and the unknown. Each journey through them is an act of faith, a leap into something that could be utterly transformative or terrifyingly destructive. But science fiction doesn't just stop at the mechanics of space travel. Wormholes often serve as metaphors for the human condition. They represent the shortcuts we wish we could take in life, the decisions we wish we could undo, the paths we want to explore but can't. In stories, stepping through a wormhole isn't just about traveling across space. It's about encountering versions of ourselves that might exist in alternate realities, facing the choices we didn't make or the futures we're afraid to confront. Wormholes in fiction carry the weight of possibility, of parallel lives and alternate timelines, reminding us of the countless ways our own stories could have unfolded differently. Science fiction has also played with the danger of wormholes, turning them into gateways not just to distant stars, but to chaos and destruction. Characters often find that wormholes are unpredictable, sometimes leading to places where the rules of physics no longer apply. There's a human vulnerability in that idea, the thought that we could create something beyond our understanding, something so powerful that it's ultimately uncontrollable. This tension is palpable in stories where wormholes lead to alien invasions, apocalyptic futures, or even to the unraveling of space-time itself. The allure of wormholes is always balanced by the threat they pose, a reminder that while we crave discovery, the unknown is never without risk. In some stories, wormholes blur the line between science and magic, becoming almost mystical in their nature. They become the means by which characters traverse not just space but dimensions of reality, where time bends or breaks, and universes fold into one another. This blending of the fantastical and the scientific speaks to a deep human desire to believe in something larger than ourselves, something that defies our current understanding yet feels within reach. Science fiction uses wormholes to stretch the imagination, pushing the boundaries of what's possible, while still grounding those stories in the familiar human emotions of fear, hope, and curiosity. At their core, wormholes in science fiction are a reflection of our hunger for exploration, for answers to the greatest questions about our place in the universe. They're an expression of the human need to push beyond limits, to imagine that there are shortcuts to the answers we seek, even if those paths are fraught with danger. They embody the essence of curiosity, the willingness to step into the unknown, no matter the cost, because the possibility of discovery is too great to resist. Whether portrayed as reliable highways through space or dangerous, unpredictable anomalies, wormholes in fiction offer us a glimpse into the boundless potential of both the universe and the human spirit. When imagining wormholes in higher dimensions, it can feel like you're stepping into a realm where human perception falters. Our brains are accustomed to three-dimensional space. Adding a fourth, fifth, or even higher dimension begins to blur the lines between what we understand and what might be possible. Picture reality not as a flat surface, but as a multi-layered tapestry, each layer representing a new dimension stacked atop the familiar three-dimensional world. A wormhole in this context isn't just a tunnel from one place to another, but an intricate fold in this fabric, one that threads its way through dimensions we cannot see or touch. In higher dimensions, wormholes might not be constrained by the limitations of our visible universe. They could snake through regions of space-time beyond what we know, offering passageways that link points in ways that defy our current understanding. For a person or a spacecraft passing through such a wormhole, the journey might feel instantaneous, or perhaps completely alien. Distances could warp and distort. Time itself might no longer flow in a straight line. The human element of this concept is in our struggle to grasp what it would feel like to exist, even momentarily, in these higher dimensional realms. We might imagine walking through a wormhole in four-dimensional space as something akin to shedding the boundaries of the physical world, experiencing sensations, colors, or forms that have no analog in our everyday life. There's a humbling feeling in considering that if these structures exist, they're hidden away in dimensions just out of reach, suggesting a universe far more complex than we've ever perceived. The mathematics behind these wormholes taps into ideas from string theory and M theory, which propose that the universe operates in more than three dimensions. Wormholes in this framework are like secret passageways through these extra dimensions, bending space-time in ways that could allow faster-than-light travel or access to distant galaxies in the blink of an eye. The possibility that higher dimensional wormholes could also serve as shortcuts to other universes hidden from us opens up a tantalizing thought. What if everything we experience is just a fraction of what's really out there? For a traveler, a wormhole in higher dimensions could be disorienting. You might step into one and feel as though you've been plucked out of the known universe entirely, passing through an abstract, invisible realm where gravity, time, and space twist into shapes beyond comprehension. You'd return to a familiar place, perhaps, but not without being profoundly changed. Your mind stretched by the experience, aware that there are levels of reality we've yet to even brush against. And yet, the instability of these structures looms large. Navigating a wormhole, especially one linked to higher dimensions, could be an impossibly dangerous task. The forces required to keep it open, the unknown physics governing its existence, might collapse the tunnel before you even pass through it. There's an inherent risk, a sense that the universe, in all its complexity, isn't designed with the human experience in mind, but that doesn't stop us from imagining, or perhaps one day, from exploring. The idea of artificially creating a wormhole feels like something torn straight from the realm of the impossible, a dream that humanity keeps chasing despite the overwhelming odds. It's the kind of concept that both fascinates and terrifies, constructing a tunnel through the very fabric of space-time, bending reality itself to our will. The notion of making something so unstable, so delicate, with our own hands, is both exhilarating and daunting. Imagine the sheer scale of ambition required to even consider the engineering of such a phenomenon, where every law of physics we hold sacred could be manipulated or possibly broken. To build a wormhole artificially would mean delving into areas of science that currently exist only on the fringes of what we know. Quantum mechanics, general relativity, exotic matter. It's like trying to craft something from the raw building blocks of the universe itself, where time and space are not constants but variables that can be twisted and molded. Exotic matter, with its strange properties of negative energy, becomes essential. Without it, the wormhole would collapse under the crushing weight of space-time's natural tendency to close in on itself. But obtaining, let alone controlling such matter, is a challenge of unimaginable proportions. This exotic material isn't something you can simply scoop up. It's theoretical, elusive, the stuff of equations, not something that we can touch or harness. Yet without it, any attempt to stabilize a wormhole would be like trying to hold open the ocean with your bare hands. But let's imagine we find a way, through breakthroughs we can barely begin to predict, to create this kind of matter. The construction of a wormhole would demand technology on a scale that feels beyond anything we've ever built. Massive energy sources would be required to warp space-time, energy perhaps equivalent to what's unleashed in the heart of a star. The creation of such a tear in the universe would have to be precise, down to the finest quantum detail, because any misstep would cause the wormhole to collapse in on itself, or, worse, lead to catastrophic consequences. A ripple in space-time that could stretch far beyond the immediate area, warping the very reality around it. Yet the human element in all of this cannot be ignored. If we were capable of creating a wormhole, what kind of society would we have to be to even wield such a tool? Would we be more enlightened, ready to explore the farthest reaches of space with wisdom and restraint? Or would we turn this incredible achievement into a weapon, an instrument of power and control? The moral and ethical dilemmas of creating wormholes are as vast as the scientific challenges. To hold the key to instant travel across the universe, or to other universes, gives humanity an unparalleled responsibility, one that we might not yet be equipped to bear. The creation of a wormhole also ties into a deeper philosophical question about control. The universe, in all its vastness and complexity, operates according to principles far beyond human command. The act of creating a wormhole is, in a way, an act of defiance, an attempt to wrest control from the natural order, to say that we are not content with the boundaries set by the cosmos. And in doing so, we would be opening the door to unforeseen consequences. If we manipulate space-time on such a fundamental level, how would that affect everything else? What would happen to causality, to the flow of time, to the very nature of existence itself? Yet despite all the risks, there's something inherently human about the idea. We are explorers by nature, and the artificial creation of wormholes would be the ultimate frontier, a step into the unknown, with all the courage, curiosity, and fear that entails. It would represent our deepest desire to understand the universe, not just by observing it from afar, but by shaping it, bending it to our will, even if that means confronting forces far greater than ourselves. The energy required for wormhole travel is a concept so staggering that it pushes the boundaries of imagination. Trying to comprehend the amount of energy needed to manipulate space-time feels like standing at the edge of a vast canyon, peering into an abyss that has no clear bottom. The idea that we could tap into energy reserves capable of warping the universe's very structure is, at its core, humbling. The force necessary to keep a wormhole stable, to hold open a passage between two distant points, would dwarf anything humanity has ever known. It would make the energy released by our most powerful nuclear weapons seem like the flicker of a match in comparison. What makes it even more daunting is that we're not simply talking about powering a spacecraft or fueling a traditional engine. This is about fundamentally altering the geometry of space itself, an action so profound that it requires a new kind of thinking, one where energy isn't just a resource but a tool to shape the very fabric of reality. It's as though the universe is a piece of cloth, and we're trying to fold and puncture it using sheer force, but the cloth resists. And that resistance demands energy on a cosmic scale, likely equivalent to the mass energy of entire stars, maybe even entire galaxies, converted directly into usable power. This is where the human element comes in. If we ever approach the point where wormhole travel becomes more than theoretical, it would force us to rethink our relationship with energy itself. Imagine what it would mean to possess or harness such a resource. What if we could create that kind of power? Would it bring humanity together, pooling knowledge and technology to explore the furthest reaches of the cosmos? Or would it deepen divides, making access to this kind of energy a battleground? The ability to unlock the energy for wormhole travel could reshape civilization in ways we can barely predict. And then there's the stark reality of limitations. As much as we can dream about traveling through wormholes, the practicalities of generating that energy remain almost insurmountable. Even in the distant future, the logistics of such an endeavor would stretch beyond any technology or energy production we've ever developed. We would need breakthroughs that go far beyond fusion or renewable sources, perhaps tapping into dark energy, the mysterious force responsible for the universe's accelerating expansion, or manipulating quantum fields at a scale that feels like science fiction today. Even if we manage to generate the energy, there's the challenge of using it in the right way. A miscalculation in distributing that energy could mean the collapse of the wormhole, or worse, a destabilization of space-time that could ripple out far beyond the intended destination. The precision needed would be terrifyingly exact, demanding a level of control over physics that we currently only theorize about. It's a paradox in many ways. The energy required is so vast, yet it must be wielded with unimaginable care, like holding the raw power of a star in your hands and trying to thread a needle with it. Ultimately, the energy requirements for wormhole travel represent a deep yearning within us, an echo of our most ancient instincts. It's the same drive that made early humans look to the horizon and wonder what lay beyond. But this horizon is so far out of reach, so vast, that it forces us to confront not just the limits of our current technology, but the limits of our ambition. It's not just about mastering the universe's energy, but about understanding what it would mean for humanity to take that leap, both physically and ethically. It's a journey that would challenge not just our scientific knowledge, but the very essence of what it means to be human in a cosmos so much larger and more complex than we can ever fully comprehend. Wormholes, despite their fascination and allure, remain an elusive idea, one that hasn't crossed the boundary from theory into proven fact. They're mathematical constructs, predictions that spring from the equations of general relativity, where the rules that govern the universe allow for such a possibility. But as of today, no wormhole has ever been observed, and no experiment has confirmed their existence. It's as if we're staring at an intricate puzzle with a crucial piece missing. We know the theory is sound, we know the potential is there, but without direct evidence, wormholes exist only in the abstract, in the realm of what if. What's interesting about the human element of this idea is our relentless drive to prove what we can't see. For centuries, we've taken abstract mathematical concepts and transformed them into physical discoveries. Black holes, for instance, were once theoretical too, spoken of in equations long before they were detected. We now have images of them, a direct confirmation of what was once only a distant idea. Wormholes may very well follow the same path, though they represent an even greater challenge, not just to observe, but to comprehend. It's a strange feeling, isn't it? To think that something so potentially powerful, so transformative, might be out there somewhere, hidden in the folds of space-time, just beyond our grasp. We've grown accustomed to thinking of space in terms of stars and galaxies, vast distances we can't cross. But if wormholes exist, they suggest there's a way to bypass all that. A cheat code in the fabric of the cosmos. And yet, we've found no sign of them. No light bending in unexpected ways, no strange gravitational effects that might hint at a hidden passage through space-time. Part of the reason for this absence of proof is the sheer difficulty of even knowing where to look. Wormholes, if they do exist, may be microscopic, tucked away at scales far smaller than we can currently observe, or they might exist in regions of the universe we've never thought to explore. Some theories suggest they could be connected to black holes, but even then, the energies and conditions required to detect or travel through them would be unlike anything we've ever encountered. There's something deeply human in our search for these cosmic mysteries, in our refusal to let them remain mere possibilities. We want proof, something tangible we can point to and say, yes, it's real. But wormholes, like so many other mysteries of the universe, resist our attempts at confirmation. It's as if they're teasing us, forever just out of reach. And in a way, that makes the pursuit even more tantalizing. The fact that we haven't proven their existence doesn't make them any less captivating. It only makes the dream of one day finding them more profound. A black hole and a wormhole, while both tied to the bending and twisting of space-time, exist on very different ends of the cosmic spectrum. A black hole is a place where gravity pulls so intensely that not even light can escape. It's like an endless pit, a point of no return where anything that crosses its boundary, the event horizon, is lost to the depths of the singularity. An incomprehensibly dense point where the known laws of physics break down. It feels final, irreversible, as though it's a place where time and space simply cease to be meaningful in the way we understand them. You can picture a black hole as a trap, a cosmic predator that devours anything unfortunate enough to get too close, forever hidden from view beyond the veil of light. A wormhole, on the other hand, is less about destruction and more about passage. Theoretically, a wormhole is a tunnel through space-time, a bridge that could connect two distant points in the universe, or even two different universes altogether. Unlike a black hole, which swallows everything, a wormhole, if stable, could allow something to travel from one side of the universe to another in an instant, bypassing the vast distances in between. It's like stepping into one door and immediately walking out of another, impossibly far away. Where a black hole is an end, a wormhole feels like a potential beginning, a gateway to the unknown. What's deeply intriguing is how both these phenomena represent opposite relationships with space-time. A black hole warps and pulls at the fabric, collapsing it inward, trapping everything in a relentless downward spiral toward the singularity. Meanwhile, a wormhole bends that same fabric in such a way that it folds back on itself, creating a shortcut across the universe. It's like comparing the finality of falling into a chasm with the hopeful possibility of tunneling through a mountain. The black hole offers no return, no escape. A wormhole, in theory, is all about the idea of escape and travel. Now imagine being near either of these cosmic wonders. The black hole would feel like a lurking force, something dark and mysterious, always pulling, always drawing you closer, but never letting go. You could feel the intensity of it, the inescapable gravity that would crush you long before you reached its core. A wormhole, in contrast, would feel like the unknown, inviting but dangerous. There's the promise of something on the other side, a destination you can't see but know might exist. Yet the risks of instability and collapse loom large. You might emerge somewhere distant, or you might be torn apart by the forces keeping the tunnel open. The human element here is how both these objects reflect our fascination with the boundaries of existence. Black holes embodying the ultimate end, the collapse of everything into nothingness, and wormholes representing the possibility of connection, of finding new worlds or entirely different dimensions. One is the darkness at the edge of our universe, the other a potential bridge across it. Both challenge us to rethink our place in the cosmos, and both remind us of how little we truly understand about the deeper layers of reality. Wormholes, as tantalizing as they are, bring with them the possibility of time travel, something that feels like it belongs more in the pages of science fiction than in the realm of physics. But the strange thing is, the math doesn't rule it out. Wormholes, if they exist and if they can be traversed, could, in theory, allow for journeys not just across vast distances in space, but across time itself. The very structure of space-time is intertwined with the flow of time, so manipulating one might give us access to the other. It's the kind of idea that feels almost too surreal to grasp, like touching the edges of a dream. But the thought of using a wormhole for time travel is where things get messy. Time, as we experience it, moves forward in a straight line, from past to present to future. But a wormhole could allow you to step off that line, bending time into something more like a loop. You could enter one end of the wormhole and emerge not just at a different place, but at a different time, maybe in the future or even the past. The possibility of walking through a door and emerging in a time you never lived is both exhilarating and terrifying, like holding the very essence of history and the future in your hands. Yet, time travel through wormholes isn't without its problems. The idea of paradoxes looms large. What if you traveled back in time and altered something critical? The classic thought experiment of going back and preventing your own birth, or causing it, becomes a real question. Would the universe allow for such contradictions, or would it find a way to protect causality? These paradoxes raise the unsettling idea that time might not be as flexible as wormholes suggest. Even if we could use a wormhole to travel to the past, the universe might have mechanisms in place to prevent any meaningful changes, locking history into a fixed path. The technical challenges of using a wormhole for time travel are just as daunting. Keeping a wormhole open and stable is already a monumental task, requiring exotic matter with properties we've only theorized about. Adding time travel into the mix brings new levels of complexity. You would have to create the conditions where the two ends of the wormhole are not just separated in space, but in time as well. The energy requirements for such a thing would be almost unfathomable, like trying to harness the power of entire galaxies just to keep the passageway intact. But the human part of this question is perhaps the most compelling. The possibility of time travel touches something deep within us, a desire to rewrite our own stories, to undo past mistakes, or to witness moments of history long gone. It's the ultimate what-if scenario. Yet, as much as we might dream about it, there's a lingering sense of caution. Would we be ready for the consequences? Time, in its unyielding march, might not be something we should play with. The temptation to see into the future or to change the past might be too great, and we don't fully understand how even small alterations could ripple out, affecting not just us, but the fabric of reality itself. So, could wormholes be used for time travel? In theory, yes. But the gap between theory and practice is immense. It's one of those possibilities that captures the imagination while reminding us that some doors, once opened, might lead to places we're not yet prepared to go. The universe may well have hidden paths through time, but whether we'll ever walk them, or whether we should, remains one of the great unknowns. Exotic matter is like the ghost of the physics world, a kind of substance that defies the familiar rules we know so well. Unlike ordinary matter, which has positive mass and follows the laws of gravity, exotic matter does something entirely different. It's thought to possess negative energy or negative mass, meaning that instead of attracting other matter like everything around us does, it would repel it. The very idea sounds as if it comes from a world that runs backward, where what we know about physics gets flipped on its head. But as strange as it is, exotic matter holds the key to something even more profound: the possibility of stable, traversible wormholes. The reason exotic matter is so important for wormholes is that it acts like a cosmic scaffold. A wormhole, without something to hold it open, would almost immediately collapse. The immense gravitational forces would pull it shut faster than anything could pass through, like trying to keep a hole open in the ocean without water rushing back in. But exotic matter, with its peculiar properties, can push against the walls of the wormhole, counteracting gravity and stabilizing the tunnel. It's as if you're trying to hold open a portal through space-time, and exotic matter is the only thing strong enough to resist the universe's natural tendency to snap it closed. What's incredible about this is the glimpse it gives into a possible future. If exotic matter could be harnessed, we could theoretically create stable wormholes, shortcuts through the vast distances of space, or maybe even through time. The dream of traveling instantly to distant stars or crossing from one side of the universe to the other suddenly feels less like fantasy and more like a challenge. Exotic matter becomes the linchpin, the thing that could turn wormholes from wild speculation into something real, something tangible. But there's a deep uncertainty that comes with this. Exotic matter isn't something we've ever directly observed, at least not in the amounts needed for wormholes. It's a theoretical concept, an idea that solves the equations but hasn't been found in the physical universe. The question of whether it exists or can be produced hangs in the air like an unsolved mystery. If it's real, then we stand at the brink of one of the most extraordinary discoveries in the history of science. If it's not, then the possibility of traversible wormholes might remain forever locked away in the realm of theory. For humans, the pursuit of exotic matter touches something fundamental: the desire to bend nature to our will, to turn what seems impossible into reality. It speaks to our relentless curiosity, our drive to find a way through the limitations imposed by the universe. The search for exotic matter is more than just a scientific quest. It's a metaphor for how we've always pushed beyond what we know, reaching out into the unknown in hopes of finding something that changes everything. So while exotic matter might seem abstract or distant, it represents the promise of the future. It's the material that could unlock the secrets of wormholes and allow us to explore the universe in ways that feel unimaginable today. But at the same time, it reminds us of how much we still don't know, how the universe holds mysteries that, for now, remain just beyond our reach. Exotic matter sits at the edge of that mystery, waiting for us to discover whether it's a path to new worlds or simply another idea that lives only in our imaginations. Traveling through a wormhole would be nothing short of bending time and space in ways that feel almost alien to our everyday experience. If you imagine space-time as a vast fabric stretched out across the universe, a wormhole would be like pinching two distant points on that fabric together, creating a tunnel that connects them. As you step through the wormhole, you wouldn't be moving in the conventional sense, traveling across space as we normally do, but rather jumping from one point in the universe to another instantly, bypassing the distance in between. The entire concept redefines how we think about motion, distance, and the flow of time. Time itself would behave strangely inside the wormhole. Our experience of time is tied to the structure of space-time, and when that structure is distorted, like it is in a wormhole, so too is time. Inside the wormhole, you might experience time passing at a normal rate, but from the perspective of an outside observer, things could appear very different. The time dilation effect, a phenomenon tied to Einstein's theory of relativity, could make it seem as if time is moving more slowly or quickly depending on the conditions. It's like being in a bubble where the rules of time don't align with the rest of the universe. What makes the whole experience even more curious is the possibility of arriving at a destination before you even left. Wormholes, if they connect not just 2 points in space but 2 different points in time, could allow for time travel. You could enter one end of the wormhole and emerge in the past or future. The idea of stepping through a door and finding yourself in a different era is both exhilarating and unnerving. It would raise deep questions about causality and whether time is something that can be shaped or altered, rather than simply followed. The space you emerge into might feel familiar, yet different, as though you've skipped over vast stretches of the cosmos without ever noticing. The stars and planets that once seemed unreachable would suddenly be within your grasp. What once took light years of travel could now be covered in the blink of an eye. But this ability to shortcut through space also forces us to rethink the very structure of the universe. Is space something we can manipulate, fold, and bypass? Or is it something more rigid, only pretending to be flexible when we think of wormholes? The sensation of traveling through such a tunnel would likely be beyond anything we've experienced. The passage could feel like an instant, a smooth leap from one reality to another, or it might be more turbulent as the forces holding the wormhole open struggle to maintain stability. There's also the terrifying prospect that the wormhole could collapse while you're inside, trapping you in a space where the laws of physics no longer apply. The danger of such an unknown journey is part of its allure, a reminder of how much of the universe remains a mystery. The human element in all this is one of curiosity and daring. We've always sought to push the boundaries of what's possible, to travel farther and faster, and wormholes would represent the ultimate step in that journey. They offer a kind of cosmic freedom we can barely comprehend, allowing us to traverse not just space, but time itself, in ways that break the rules we thought were unbreakable. But along with that freedom comes risk. The risk of changing things we don't fully understand, of bending time and space in ways that could have unforeseen consequences. So, traveling through a wormhole wouldn't just affect time and space. It would change how we relate to the universe itself. It would open up possibilities for exploration and discovery, while also challenging our understanding of reality. We would be stepping into a realm where the familiar rules no longer apply, where time could slip through our fingers, and where the very fabric of existence bends and twists in ways we can't yet predict. Wormholes, by their very nature, are fragile constructs in the fabric of space-time. They're like tenuous bridges between distant points, held together by forces that we barely understand. The concept of a wormhole is born out of the mathematics of general relativity, but that same math reveals just how unstable they are. Left to their own devices, a wormhole would almost certainly collapse before anything could pass through it. The immense gravitational forces that hold open the tunnel between 2 points would cause the walls to snap shut, faster than we could imagine, effectively destroying any hope of using them for travel. The instability of wormholes comes down to the shear forces at play. The gravity inside the wormhole is so intense that it would pull everything inward, like a black hole pulling on anything that crosses its event horizon. This gravitational collapse would make the wormhole useless, as it would seal itself off from both ends almost immediately. In this sense, wormholes seem to be fleeting phenomena. If they exist at all, vanishing before we could even attempt to interact with them. It's like trying to keep a hole open in a waterfall, only to have the torrent crash down and close it the moment you step away. But there's a sliver of hope in this seemingly impossible situation. The idea of exotic matter, with its negative energy, offers a possible solution. If we could place exotic matter inside a wormhole, it could act as a counterbalance to the crushing forces of gravity, pushing against the walls of the tunnel and keeping it open. The exotic matter would effectively stabilize the wormhole, preventing it from collapsing long enough for something, or someone, to pass through. This is where the dream of traversible wormholes begins to feel more tangible, but also where the challenge becomes even more daunting. Exotic matter is purely theoretical, and we've never observed it in the quantities needed to stabilize a wormhole. The potential for stability depends on finding this elusive exotic matter, which could be as rare and as strange as the wormholes themselves. Even if it exists, controlling it and manipulating it in the precise way needed to hold a wormhole open would be a task of unimaginable complexity. It's as if the universe is offering us a glimpse of a door that could take us to far-off places, but it's locked behind layers of puzzles that we haven't yet solved. And even if we could stabilize a wormhole, there's the question of how long it would last. Would it remain open indefinitely, or would it be a temporary gateway, only stable for a brief moment before collapsing again? The instability of wormholes also brings with it the risk of catastrophic failure. If the exotic matter were to falter, or if the balance of forces were to shift, the wormhole could collapse while someone or something was inside. The thought of being caught in such a collapse is terrifying, trapped in a space where the very rules of physics might break down. It's a reminder that wormholes, for all their potential, are not just pathways to other places but dangerous, unstable phenomena that could just as easily destroy as they could connect. For humans, the idea of stabilizing a wormhole is like a beacon of possibility, a way to break free from the limitations of space and time. But it's also a stark reminder of how precarious the endeavor would be. The balance required to keep a wormhole open is delicate, and the forces involved are vast and unforgiving. It's a dream that pushes the boundaries of what we understand, and yet it's filled with uncertainty. An idea that's both exhilarating and filled with the risk of collapse, in every sense of the word. Quantum physics takes the whole idea of wormholes and spins it into a realm even more perplexing and intricate than before. On the surface, wormholes are creatures of general relativity, describing how the warping of space-time might allow for tunnels that connect distant regions of the universe. But when quantum mechanics steps in, things start to get even more mind-bending. The strange and often counterintuitive world of quantum particles, their ability to exist in multiple states at once, their entanglements that defy classical logic, begins to interact with the fabric of space-time in ways that are not yet fully understood. One of the key roles quantum physics plays in wormhole theory is through the concept of quantum entanglement. Imagine two particles, no matter how far apart they are, being linked in such a way that the state of one instantly affects the state of the other. This bizarre connection, which Einstein once called spooky action at a distance, is one of the most mysterious aspects of quantum theory. Some physicists believe that quantum entanglement could be connected to the idea of wormholes on a fundamental level. Theorists like Juan Meldacena have proposed that perhaps wormholes are essentially the geometrical manifestation of entangled particles. It's as if, on a deep quantum level, the universe is stitched together not just by the forces of gravity and space-time, but by the very strange and subtle entanglements of particles themselves. Wormholes, in this view, could be nature's way of making those connections tangible. The influence of quantum mechanics doesn't stop at entanglement. Quantum fluctuations, tiny, temporary changes in energy that occur everywhere, even in the vacuum of space, add another layer of complexity. These fluctuations suggest that space-time itself may not be a smooth fabric, but a seething, frothy ocean of tiny, fluctuating wormholes, too small for us to detect. These microscopic wormholes, sometimes called quantum foam, might pop in and out of existence at scales far beyond our current technological reach. While these quantum-scale wormholes wouldn't be traversible for us, they hint at a universe where wormholes might be as common as air molecules, just hiding on a level we can't perceive. It's a vision of space-time that's dynamic and alive, not just a static backdrop. Yet, as tantalizing as these quantum effects are, they also raise deep questions about the stability of wormholes. On the quantum level, nothing is ever truly at rest. The very laws that govern quantum physics seem to imply that wormholes, particularly at larger scales, could be incredibly unstable without something like exotic matter to counteract the quantum fluctuations. The interplay between the two realms, classical general relativity on one hand and the strange dance of quantum mechanics on the other, is one of the great unsolved problems in physics. It's here that the dream of unifying these theories into a quantum gravity becomes more than just an academic exercise. It might be the key to understanding whether wormholes could ever become a reality we can interact with. For humans, the involvement of quantum physics in wormhole theory feels like walking into a room where the walls, floor, and ceiling are constantly shifting. Everything we thought we knew about space and time starts to blur as quantum uncertainty and relativity overlap. The question isn't just whether wormholes could exist, but how they would behave in a universe that's ruled by both the large-scale forces of gravity and the tiny, unpredictable rules of the quantum world. Traveling through a wormhole might not just warp space and time. It could also thrust us into an environment where the very fabric of reality pulses with quantum strangeness. This quantum layer of wormholes is what makes the theory so compelling, yet so elusive. The answers, if they exist, lie buried in the intersection between these two fundamental aspects of our universe. An intersection that, for now, remains hidden from us, waiting to be uncovered by minds bold enough to ask the most difficult questions about reality. In the search for those answers, quantum physics offers the possibility that wormholes aren't just theoretical constructs but part of a deeper, more connected universe than we ever imagined. Wormholes, in theory, are like bridges or shortcuts through the fabric of space and time, tunnels that connect two distant points in our universe. But what if they could connect more than just points in space? What if they were pathways to parallel universes, alternate realities where the rules might be slightly, or drastically, different? This idea stretches beyond science fiction and reaches into the realm of possibility through the mathematics of general relativity. The concept of parallel universes, sometimes called the multiverse, suggests that there are other realities existing alongside our own, each one perhaps governed by different laws of physics or histories. If wormholes could connect these alternate universes, it would mean that, in some sense, we are not confined to the reality we experience. Picture it, somewhere, out there. If out there even makes sense in this context, there might be another version of you, living a slightly different life, making slightly different choices. It's both awe-inspiring and unsettling to think about. We are creatures shaped by the reality we know, by the moments we've lived, the people we've met, and the forces that govern our world. To imagine that there are entirely different versions of this reality, inaccessible yet right next to us, forces us to confront the limits of our understanding. But the idea of wormholes linking these parallel worlds isn't just a thrilling thought experiment. It's also a deeply human one. We are always searching for connection, for understanding, for a way to bridge the gaps between the known and the unknown, between ourselves and the world around us. Wormholes, in this context, can be seen as a metaphor for our desire to break through those boundaries, to reach beyond what we know and discover something more, something beyond the constraints of our universe. However, wormholes are incredibly unstable, at least as we understand them now. Even if they existed, keeping one open long enough to pass through, let alone reach another universe, would require vast amounts of energy, perhaps beyond what we can even imagine harnessing. It's not just a technological hurdle, it's a conceptual one. We don't even know for sure if these parallel universes exist, much less how to traverse them. Still, the idea lingers, nudging at the edges of what might be possible. What would it be like to peer through such a wormhole? Would the other side be familiar, a warped version of our own world, or utterly alien, incomprehensible to our senses? The thought of wormholes linking parallel universes taps into something deeply personal. It reflects our desire to explore the unknown, to break out of the confines of our own reality, and to find out what lies beyond. It's not just about physics or science fiction. It's about the human drive to connect, to reach beyond the stars, beyond time, and perhaps even beyond the universe itself. In our everyday lives, we search for those kinds of connections too, sometimes without even realizing it, whether it's through relationships, creativity, or pushing the boundaries of what we think we know. At its core, the idea of wormholes linking parallel universes isn't just about alternate realities or hypothetical physics. It's about human curiosity, the urge to discover what's on the other side of the unknown, and the wonder that comes with knowing there might always be something more just out of reach, waiting to be found. Wormholes fit into the concept of the multiverse as potential gateways, not just between different locations in our own universe, but between entirely separate universes themselves. It's almost as if they offer a way to stitch together the fragments of reality, which otherwise remain inaccessible to one another. The multiverse theory suggests that there could be an infinite number of universes, each one a different expression of physical laws, or perhaps even slightly altered versions of our own reality. These universes exist alongside each other, yet never interact, unless something like a wormhole creates that bridge. Wormholes provide the tantalizing possibility that these isolated universes aren't as isolated as they seem, that there's a way to travel between them, even if it's through a method far beyond our reach for now. When thinking about this, it's hard not to compare it to the way we experience the world on a personal level. We live our lives within the boundaries of our own experiences and perceptions, much like a universe unto ourselves. We catch glimpses of other people's realities, but we never fully cross into them. The multiverse theory is like that, except on a grand, cosmic scale, where entire universes are separated by unseen barriers, each self-contained and unaware of the others. A wormhole, in this context, represents a rare chance to cross those boundaries, to step into another version of existence, even if it's just for a moment. In many ways, wormholes are more than just mathematical curiosities. They reflect our deepest questions about reality and existence. If a multiverse exists, the idea of a wormhole connecting these separate realities brings the possibility of interaction into the realm of the imaginable. And if there's a way to traverse these boundaries, what might we find on the other side? The concept is strangely intimate in a way, because it forces us to think not just about our universe as a whole, but also about ourselves as individuals, confined to our own worlds yet constantly seeking to bridge the gap between the known and the unknown. In a multiverse connected by wormholes, each universe would be like an isolated island, but with hidden pathways that allow for the rarest and most extraordinary kinds of travel. What might start as a theoretical physics question becomes something almost philosophical. Could other versions of ourselves exist in these parallel universes, making different choices, living different lives? And if a wormhole could link us to those lives, how would that change our understanding of who we are? It's a question that touches not just on science, but on the essence of identity and experience. It's one thing to imagine an endless array of disconnected universes, but the idea of wormholes connecting them suddenly makes those universes feel much closer, much more real. It shifts the conversation from one of pure abstraction to something almost tangible. It invites us to consider not just the boundaries of space and time, but the boundaries of existence itself and how fragile or permeable those boundaries might actually be. Wormholes, then, aren't just theoretical pathways. They're a reflection of our endless curiosity and our refusal to accept that some things must remain out of reach forever. In thinking about wormholes within the multiverse, we're reminded of how much of the universe, and perhaps other universes, we still don't understand. And yet, at the heart of this mystery is the very human desire to explore, to connect, and to see what lies beyond the limits of what we can comprehend. Just as wormholes might thread together distant corners of the multiverse, our minds are constantly trying to weave together the fragments of reality that feel separate and out of reach, searching for that elusive connection that could change everything. The idea of creating or opening a wormhole artificially feels like something pulled straight from the farthest reaches of science fiction, but there are kernels of real science behind the notion. Wormholes, as predicted by Einstein's theory of general relativity, are theoretically possible. Yet the question of whether we could ever build one or force one open is wrapped in layers of complexity that we've only just begun to understand. At its core, the creation of a wormhole would require an enormous amount of energy, more than anything we've ever harnessed or even dreamed of controlling. Some theories suggest that exotic matter, stuff that has negative energy, would be necessary to stabilize a wormhole, preventing it from collapsing in on itself the moment it was formed. Exotic matter isn't something we've encountered yet in any tangible form, making the whole concept of creating a wormhole feel like reaching for the impossible. But humanity has always been about reaching for the impossible. It's in our nature to push against the limits of what we know and to imagine what could be possible with just a little more understanding, a little more innovation. The question of artificially opening a wormhole is as much about our ambition and curiosity as it is about the laws of physics. If we could find a way to access the kind of energy or materials necessary to create a wormhole, it would be a breakthrough on a scale that's difficult to comprehend. It would mean that we could manipulate the very fabric of space-time, bending it to our will, opening doorways to parts of the universe, or maybe even other universes, that are unreachable through any other means. Of course, the challenge is immense. The forces involved in creating a wormhole are not like anything we've ever encountered. Black holes, where space-time is warped to an extreme degree, are the closest natural example we have, and they are terrifying in their power and destructive potential. Trying to artificially recreate something akin to that, but stable and safe enough to travel through, would require leaps in technology and physics that seem almost unimaginable today. But almost unimaginable has never stopped us before. When you look at the history of human innovation, it's filled with moments where something that once seemed like pure fantasy became reality, sometimes through sheer will and determination. The possibility of creating a wormhole also forces us to consider the ethical and philosophical implications. If we ever reached the point where we could open such a portal, what would it mean for how we understand our place in the universe? Would we be able to explore distant galaxies or parallel dimensions, or would the risks outweigh the rewards? There's something profoundly human about this line of questioning, because it's not just about the science. It's about how that science would shape our future, our decisions, and even our sense of identity. The power to create a wormhole, to literally bend reality, is also the power to change everything we know about our world and our role in it. But for now, the creation of a wormhole remains a distant, speculative dream. We're still far from understanding all the intricacies of how space-time works, let alone how to manipulate it on such a colossal scale. Yet, that spark of possibility is enough to keep us wondering. Could we one day create these cosmic gateways? Could we master the forces needed to bend space and time to our will? It's a question that speaks to both our technical ambition and our deep desire to explore beyond the boundaries of what we know. And even though the answer remains elusive, the fact that we're even asking the question is a testament to the boldness of human imagination. The amount of energy required to keep a wormhole open is something that stretches the imagination, pushing it to the extremes of what we understand about physics. Wormholes, if they exist at all, would be incredibly unstable, collapsing in an instant without something to keep them from imploding under the weight of their own gravity. To stabilize one, it's often theorized that we would need exotic matter, a substance that doesn't follow the usual rules of physics. Exotic matter would have negative energy density, something that feels almost paradoxical, as we've never encountered it in any practical way. It's like trying to hold open a doorway against the weight of an entire mountain. Only that mountain is the vast, incomprehensible force of space-time itself, constantly trying to snap the wormhole shut. The energy required to keep a wormhole open might not just be large. It could be astronomical, dwarfing any energy sources we currently have access to. Some estimates suggest that it would require energy on the scale of an entire star's output, maybe even more. That's hard to comprehend, because even our most powerful machines today are like candles compared to the energy a star produces. We're talking about orders of magnitude beyond anything humanity has ever dealt with, something closer to the raw forces of the universe itself, like the energy released in a supernova, where stars explode and give off more energy in a few seconds than our sun will in its entire lifetime. It's easy to throw out numbers like the energy of a star, but what does that really mean on a human scale? Imagine trying to power a machine that consumes more energy in a second than all of human civilization could produce in thousands of years. Even our most ambitious dreams of energy production, like harnessing the power of fusion, feel small in comparison to what would be needed to hold a wormhole open. And it's not just about generating that energy. It's about controlling it, channeling it in a way that doesn't tear everything apart in the process. The idea of controlling such vast amounts of energy feels almost mythical. It's a bit like trying to contain the ocean in a glass, an attempt to harness forces that are naturally beyond us. Yet, the very fact that we can think about these things, theorize about them, and wonder how they might be achieved, speaks to the boundless curiosity and ambition that drives us. Even if keeping a wormhole open requires energy beyond what we can currently produce or even imagine, we've never been a species that shies away from seemingly impossible challenges. The idea of stabilizing a wormhole might sound like pure fantasy now, but then again, so did the idea of harnessing nuclear energy a century ago, or traveling to the moon. Human history is full of moments where the impossible became possible through the relentless pursuit of knowledge and the unshakable belief that there is always more to discover. The energy needed to keep a wormhole open may be staggeringly vast, but that just means the challenge is bigger, not insurmountable. The energy required also makes us think about the consequences. If we could find a way to generate and control that kind of power, we would be unlocking forces that could reshape our understanding of reality, but also ones that could be incredibly dangerous. What happens if you don't get the balance right? Could an unstable wormhole unleash forces that tear apart the very fabric of the universe? These are questions we would have to answer, and they're questions that tie directly into the human experience. The risk, the curiosity, and the ever-present hope that we can find a way to do the impossible without destroying ourselves in the process. For now, the idea of producing enough energy to keep a wormhole open remains theoretical. It's a problem for the distant future, a challenge that will require not just new technologies, but entirely new ways of thinking about energy, space, and time. But the thought of it lingers, because if we ever could manage to keep one of these cosmic doorways open, the universe itself might become a very different place for us, one filled with possibilities we can only dream of today. The idea that microscopic wormholes might exist around us, perhaps flickering in and out of existence, feels like something pulled from the deepest reaches of imagination. But in theoretical physics, it's not as far-fetched as it sounds. Some models suggest that, at the quantum level, space and time might not be smooth and continuous as we experience them, but rather a seething, chaotic sea of fluctuations. In this quantum foam, tiny wormholes, infinitesimal tunnels through space-time, could potentially pop into and out of existence, like bubbles appearing and disappearing in boiling water. They would be so small, perhaps at the Planck scale, that we wouldn't notice them. They'd be far smaller than atoms, smaller even than the particles that make up atoms. These wormholes, if they exist, would be hidden in the very structure of reality itself, woven into the fabric of existence on a scale so tiny that our current technology can't detect them. It's a strange thought, isn't it? That there could be these hidden connections, right in front of us, yet completely out of reach. Microscopic wormholes might not be something we could ever interact with directly. They'd be fleeting, unstable, opening and closing in such a short span of time that they barely exist at all. And yet, their presence could have profound implications for how we understand the universe. In some speculative theories, these tiny wormholes might allow for instant connections between different points in space-time, though only on a microscopic scale. They wouldn't be portals for people or even particles, but their existence would suggest that space itself isn't as rigid as we tend to think. This opens the door to a more complex picture of reality. If microscopic wormholes are part of the structure of the universe, it implies that space-time is a lot stranger than our everyday experience suggests. We walk through life assuming that the space around us is empty, that time moves forward in a straight line. But if these tiny wormholes are there, even for the briefest moments, they tell a different story. One where space can loop back on itself, where time can twist and fold in ways we don't yet understand. It's like knowing that beneath the calm surface of a pond, there's an entire world of swirling currents and hidden depths, even if we can't see them. At the same time, it's a reminder of how little we know about the universe on the smallest scales. We've made incredible progress in understanding the cosmos, but the quantum world remains full of mysteries. If microscopic wormholes are real, they exist in a realm that is still mostly beyond our grasp. It's humbling to think that these tiny tunnels, these potential shortcuts through space-time, could be all around us, quietly existing without us ever being aware of them. It's like realizing that the world is much bigger, or in this case much smaller, than we ever imagined. The human element in this is our constant need to push the boundaries of what we know. We've always been fascinated by what's hidden, by the invisible forces that shape our reality. The thought of these tiny, ephemeral wormholes sparks that same curiosity. Could they hold the key to new understandings of physics? Could they be the beginning of some future breakthrough in how we manipulate space and time? It's not that we expect to travel through these microscopic wormholes. They're too unstable and too small for that. But just knowing they're there would change how we think about the universe and our place in it. In the end, the existence of microscopic wormholes, if proven, would be another reminder that the universe is layered with mysteries, some of which are so subtle and fleeting that they slip right past us. Yet we continue to search, driven by that uniquely human desire to understand the hidden workings of everything around us. It's a quiet, almost invisible frontier, but one that might hold answers to questions we haven't even thought to ask yet. Wormholes, while fascinating in theory, come with an array of dangers and paradoxes that challenge our understanding of reality. The first and most obvious danger is their inherent instability. A wormhole, by its nature, is a bridge between distant points in space-time, but it's not a stable one. Without some kind of exotic matter to keep it open, it would likely collapse the moment anything tried to pass through. That collapse could be catastrophic, with the immense gravitational forces at play potentially tearing apart anything, or anyone, caught inside. Even if we manage to stabilize a wormhole, the sheer unpredictability of space-time at such extremes means we could never be certain of what lies on the other side. It's the ultimate gamble, stepping into the unknown, not knowing if you'll emerge somewhere else or be crushed by forces beyond your control. There's also the possibility that a wormhole could distort time as much as it distorts space. This leads to one of the most famous and unsettling paradoxes, the time travel paradox. In theory, if a wormhole connects 2 points in space, it could also connect 2 points in time. What if one end of the wormhole were positioned in the past while the other remained in the present or future? This creates the potential for a time loop, where someone could travel back in time and interfere with events in a way that could lead to contradictions. The classic example is the so-called grandfather paradox. What happens if you go back in time and prevent your grandparents from meeting? Would you still exist? Wormholes, with their ability to manipulate space-time, open the door to these kinds of troubling scenarios. They challenge our linear understanding of cause and effect, forcing us to confront the possibility that time might not work the way we think it does. These paradoxes aren't just theoretical problems. They strike at the heart of what makes us human, our need for order, for continuity, for things to make sense. Time, as we experience it, is stable, a thread that connects moments into a coherent narrative. But wormholes, with their potential to warp and twist that thread, threaten to unravel the whole thing. The idea that you could change the past, or that events could loop back on themselves, creates a kind of existential anxiety. It's more than just the fear of the unknown. It's the fear that reality itself could become unpredictable, that the rules we rely on to make sense of the world might not apply in the presence of a wormhole. Then there's the question of what happens on the other side. If a wormhole connects distant regions of space, or even different universes, there's no guarantee that what waits on the other side is safe or even recognizable. We imagine wormholes as tunnels through which we can travel, but there's no reason to believe that space on the other side would obey the same rules as the space we're familiar with. Gravity might behave differently, the laws of physics could be altered, or the very fabric of reality could be distorted in ways that we can't predict. It's like stepping through a door into a world where all the rules have changed, and you're no longer sure of what's possible or what's safe. Beyond the physical dangers and paradoxes, there's also a psychological element to consider. What would it do to a person to travel through a wormhole, to step outside the familiar boundaries of time and space? Would it alter their perception of reality? Would they be able to return and still feel connected to the world they left behind, knowing they had glimpsed something so far beyond human experience? There's something deeply unsettling about the idea of crossing such a boundary, of venturing into a space where the normal rules don't apply. It touches on the same primal fear we feel when confronted with the vastness of space itself. The sense that, out there, the universe is far bigger and stranger than we can fully comprehend. In the end, the dangers and paradoxes of wormholes are not just about the physics involved. They reflect the limits of our understanding and the fragility of the reality we take for granted. Wormholes challenge us to rethink everything we know about space, time, and causality, and in doing so, they force us to confront our own fears about stepping into the unknown. It's the classic human dilemma, the desire to explore, to discover what lies beyond, balanced against the fear of what might happen when we cross that final, uncharted boundary. Wormholes have become a staple in science fiction, often portrayed as the ultimate shortcut across the universe, a way to bypass the immense distances that would otherwise take lifetimes to traverse. They appear as convenient plot devices, offering a sense of wonder and mystery while also solving the practical problem of how characters can move through space at faster-than-light speeds. In many stories, wormholes are depicted as stable, navigable tunnels, doorways to other galaxies, other times, or even parallel dimensions. They're often used as gateways to unknown realms, adding an element of the unknown that enhances the drama and scale of the narrative. But the way wormholes are portrayed in fiction is often a far cry from the complex and hazardous reality that theoretical physics suggests. In science fiction, wormholes are typically stable, safe passages. You see it in movies and shows like Interstellar, Stargate, or Star Trek, where characters can enter a wormhole and emerge on the other side, often in a different part of the universe or even another galaxy, with relatively little consequence. In these stories, wormholes are often treated as highways through space, something that can be navigated with the right technology. They offer a sense of freedom, an escape from the constraints of time and space, allowing characters to explore the furthest reaches of the cosmos. But this portrayal is much more optimistic than what real science would suggest. Wormholes in theory are far from stable, and the idea of traveling through one without being torn apart by extreme gravitational forces is highly speculative at best. The realism of these fictional wormholes tends to take a back seat to narrative needs. The complexity and danger of actually using a wormhole, if they exist at all, are often glossed over or reduced to background details. In reality, wormholes would require enormous amounts of energy to remain open, if they could even be stabilized at all. And even if you could keep one open, traveling through it would likely be an incredibly dangerous experience, involving forces and phenomena we barely understand. Science fiction rarely delves into the physics of what passing through a wormhole would actually feel like, whether it would be a smooth, instantaneous journey or something far more disorienting and perilous. For the sake of storytelling, most fictional accounts keep things relatively simple, allowing characters to step through a wormhole much as they would walk through a doorway. Yet, there's a reason wormholes have captured the imagination of so many writers and creators. They embody our deepest desires to break free from the limitations of our current technology and understanding. The vast distances of space are intimidating. Even with the fastest spacecraft we could imagine, reaching the nearest star would take thousands of years. Wormholes offer a way around that, a fantastical solution to the problem of cosmic isolation. In fiction, they represent hope. The idea that the universe isn't as inaccessible as it seems, that there might be shortcuts hidden in the fabric of reality itself, just waiting to be discovered. And while science fiction takes liberties with the details, there's something about the idea of wormholes that resonates deeply with our sense of adventure. The thought of stepping into a wormhole and emerging somewhere unimaginably distant is thrilling, even if we know that in reality, the concept is far more uncertain and dangerous. Wormholes in fiction often reflect the human spirit's longing to explore, to venture into the unknown and overcome the barriers that stand in our way. They are symbols of possibility, representing the dream that, with the right technology or understanding, we could one day break free from the chains of space and time. When you look at wormholes through the lens of realism, though, it becomes clear that we're nowhere near being able to create or navigate one, even if they do exist. The amount of energy required to stabilize a wormhole, the potential for catastrophic collapse, and the unknown physics of what lies within make wormholes more of a theoretical curiosity than a practical tool. But the beauty of science fiction is that it doesn't need to be bound by these limits. It allows us to imagine a future where such things are possible, where humanity can leap across galaxies in the blink of an eye, where the impossible becomes real. Wormholes, as they appear in science fiction, are more than just plot devices. They reflect our deepest desires for exploration, freedom, and discovery. And while the reality of wormholes might be much more complex and dangerous, the fact that they continue to inspire stories about the future speaks to our collective hope that one day, the barriers of space and time will no longer be so daunting. Even if wormholes in fiction aren't exactly realistic, they remind us that the universe is full of mysteries waiting to be solved, and that the human imagination is a powerful tool in its own right, constantly pushing us to dream of what lies beyond the next horizon. Wormholes, in theory, could provide a way to achieve faster-than-light travel, but not in the way you might think. They don't break the cosmic speed limit set by the speed of light, but rather bend the rules by creating shortcuts through space. If you imagine space as a vast sheet of paper, and 2 points on that paper representing 2 distant places in the universe, you would normally need to travel across the paper from one point to the other, bound by the speed of light. But if you could fold the paper so that the 2 points touch, you could step through, effectively bypassing the vast distance between them. In this sense, wormholes cheat the system, offering a way to travel faster than light would across normal space by avoiding the journey entirely. The appeal of wormholes for faster-than-light travel lies in their ability to connect 2 points in space instantaneously, or at least, so it seems. The distance between the 2 points, no matter how vast, could be traversed in an incredibly short time compared to what it would take light to cover the same distance by normal means. Theoretically, a spaceship could enter a wormhole at one point in space and emerge somewhere else, light years away, in a matter of moments. It sounds like magic, but really, it's a manipulation of space-time itself. Instead of moving through space, you're moving through the fabric of space, bending it to create a path where none existed before. But wormholes that allow for faster-than-light travel are far from guaranteed. In reality, no one knows whether such stable, traversible wormholes could exist. The concept depends on solving some of the most difficult problems in theoretical physics, and even if we could create or discover one, there's no assurance that it would stay open long enough for anything to pass through it. Exotic matter would be needed to keep the wormhole stable, and we don't yet know if such a material exists. Without that stability, the wormhole could collapse, trapping or destroying anything inside. This is where the danger becomes real. Faster-than-light travel through a wormhole may not just be difficult. It could be impossible in practice. Even if we could solve these technical challenges, the journey through a wormhole might not be the smooth, science fiction-like experience we imagine. There's the potential for massive gravitational forces, intense radiation, and all kinds of other hazards that could make wormhole travel extremely dangerous, if not lethal. The reality of faster-than-light travel, then, might look less like a swift and easy journey across the stars and more like a harrowing passage through the chaotic, unpredictable forces of the universe. What's fascinating about this idea, though, is how it stretches our understanding of space and time. The very fact that wormholes might offer a way to travel faster than light challenges what we think we know about the universe. It's a reminder that the universe isn't static and that our understanding of its laws could evolve. For now, the speed of light remains an unbreakable barrier for anything moving through normal space, but wormholes offer a tantalizing hint that there might be ways to bypass that limitation, to connect places that would otherwise be separated by unbridgeable distances. The human element in all this is our desire to overcome the limits imposed by nature. Throughout history, we've looked at the vastness of the world and the universe and asked, how can we go further? Whether it was crossing oceans or developing rockets to reach the stars, the drive to explore has always been fueled by the hope that we can surpass the boundaries that seem insurmountable. Wormholes, as a theoretical possibility, represent the ultimate boundary crossing, moving faster than light, not by speeding up, but by finding a way around the rules altogether. In the end, while wormholes offer a theoretical path to faster-than-light travel, they remain speculative at best. There are enormous hurdles to overcome, both in understanding how they might work and in developing the technology to use them safely. But the idea persists because it taps into something deeply human. The belief that, no matter how vast the universe seems, there's always a way to push further, to discover new ways of moving through the cosmos that defy the limits we know today. As we wrap up this journey through the mysteries of wormholes, I want to thank you for exploring these mind-bending ideas with me. From the intricacies of space-time to the tantalizing possibility of connecting universes, it's clear that wormholes offer as many questions as they do answers. If you enjoy diving into the unknown, don't forget to give this video a thumbs up. It helps more curious minds discover it. And if you're ready to keep exploring the cosmos and beyond, subscribe to Quiet Universe for more deep dives into the wonders of science and the imagination. Until next time, keep questioning, keep wondering, and who knows? Maybe one day, we'll find that shortcut through space and time.